Nothing was supposed to last this long. Mountains fracture, rivers change course, coastlines retreat, and entire cities disappear beneath the earth. Yet scattered across the same changing landscape are creations made by human hands that have endured for thousands of years. Giant stones still balance above valleys. Stairways climb toward abandoned temples. Tunnels vanish into mountains, while forgotten walls stretch across places where their builders are no longer remembered. Some have been studied for centuries. Others are only beginning to reveal what lies beneath them. But wherever they are found, they leave the same unsettling impression. The ancient world was capable of creating things far more ambitious, complex, and enduring than the ruins alone can explain.
Sumer is often called the world's first civilization, yet the greatest mystery surrounding it is not that it existed, but how it appeared with such astonishing sophistication. In the flat alluvial plains of southern Mesopotamia, in what is now Iraq, a people emerged more than 5,000 years ago and created cities, mathematics, writing, engineering systems, and administrative networks on a scale humanity had never seen before. What makes Sumer so fascinating is that many of its technological achievements seem to appear suddenly in the archaeological record, leaving researchers to wonder whether we're still missing crucial chapters of humanity's earlier scientific development. The story began in the 19th century when archaeologists excavating ancient mounds across Mesopotamia uncovered thousands of clay tablets covered in strange wedge-shaped symbols. Sites such as Uruk, Eridu, Lagash, and Nippur gradually revealed the remains of a civilization that had flourished between roughly 4,500 and 1900 BCE. As more discoveries emerged, scholars realized they were looking at something extraordinary. Long before the pyramids of Egypt reached their greatest form and nearly 2,000 years before classical Greece, the Sumerians had already built large urban centers, organized governments, and developed technologies that would influence the next 4 millennia of human history. One of the first puzzles concerns the sudden rise of cities. The city of Uruk may have supported between 40,000 and 80,000 inhabitants around 3,200 BCE, making it one of the largest urban centers on Earth at the time. Yet southern Mesopotamia lacked many of the resources normally associated with the growth of complex civilizations. There were few stone quarries, limited timber supplies, and almost no local metal deposits. Despite these disadvantages, the Sumerians created massive cities connected by trade networks stretching hundreds and sometimes thousands of kilometers. Archaeologists continue to debate how such large-scale urban organization emerged so rapidly. The transition from scattered farming communities to densely populated cities appears unusually fast compared with many other ancient regions. The engineering challenge facing the Sumerians was even more remarkable. Southern Mesopotamia was both fertile and dangerous. The Tigris and the Euphrates rivers provided water and rich sediments, but their flooding patterns were unpredictable. Too little water meant crop failure. Too much water could destroy entire settlements. To survive, the Sumerians constructed vast irrigation systems consisting of canals, reservoirs, levees, and distribution channels. Satellite surveys and archaeological mapping reveal canal networks extending for hundreds of kilometers. Maintaining such systems required an understanding of gradients, water flow, soil conditions, and labor management. Modern hydraulic engineers note that even small errors in elevation can significantly reduce the efficiency of irrigation systems. Yet these ancient builders achieved large-scale water management without modern surveying instruments, metal machinery, or advanced mathematical tools as we understand them today. However, the most intriguing mystery lies not in their cities or canals, but in their mathematics. Among all ancient technological achievements, the Sumerian mathematical system remains one of the most puzzling. Most civilizations naturally developed counting systems based on 10, reflecting the number of fingers on human hands. The Sumerians took a different path. They adopted a base 60 numerical system known today as the sexagesimal system. More than 5,000 years later, humanity still lives with this ancient decision. There are 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a circle because of mathematical traditions that can be traced back to Mesopotamia. The question is why? Base 60 is mathematically elegant because it can be divided evenly by many numbers, including 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This makes fractions and calculations easier than in many other numbering systems. Yet recognizing these advantages requires a surprisingly sophisticated understanding of numerical relationships. Archaeologists have discovered clay tablets showing multiplication tables, division exercises, geometric calculations, and algebra-like problem solving. Some tablets dating to nearly 4,000 years ago demonstrate mathematical reasoning that would not become common in many other societies until much later. One famous example is the tablet known as Plimpton 322. Dating to approximately 1800 BCE, it contains numerical patterns that many researchers interpret as related to right triangles and what are now called Pythagorean triples. Although debate continues regarding its exact purpose, the tablet demonstrates an advanced understanding of mathematical relationships centuries before the lifetime traditionally associated with Pythagoras. The existence of such knowledge raises profound questions about how mathematical concepts developed in the ancient world and whether earlier stages of this intellectual evolution remain undiscovered beneath the sands of Mesopotamia. The sophistication of Sumerian mathematics becomes even more impressive when viewed alongside their administrative systems. Hundreds of thousands of clay tablets have been recovered from archaeological sites throughout Mesopotamia. These records track taxes, agricultural production, trade transactions, labor assignments, property ownership, and religious offerings. Managing such enormous quantities of information required standardized numerical systems and reliable methods of calculation. Some historians describe Sumerian bureaucracy as humanity's first large-scale information processing network. Long before computers, the Sumerians had effectively created a data management system capable of organizing entire cities and kingdoms. Their achievements extended into astronomy as well. Ancient Mesopotamian observers carefully recorded celestial movements for centuries. By monitoring the moon, planets, and seasonal cycles, they developed increasingly accurate calendars. Later, Babylonian astronomers inherited and expanded this tradition, but many of its foundations likely originated with earlier Sumerian observations. Some scholars argue that the mathematical structure of the base 60 system may have been linked to astronomical calculations. The number 360, for example, closely approximates the number of days in a year recognized by some ancient calendars. Whether this connection was intentional remains uncertain, but it highlights the remarkable integration of mathematics, administration, and astronomy within Sumerian society. Another technological mystery can be seen in the construction of ziggurats. These massive step temple complexes dominated the skylines of major cities. The Great Ziggurat of Ur originally stood more than 30 meters high and required millions of mud bricks. Building structures of this scale in a region with frequent flooding and limited stone resources posed immense engineering challenges. Excavations have revealed sophisticated drainage systems layered construction techniques, and the use of natural bitumen for waterproofing. Many sections survived for thousands of years despite being built primarily from sun-dried mud brick, a material generally considered vulnerable to erosion. Modern researchers continue to study how Sumerian builders optimized materials and construction methods to achieve such durability. The mystery deepens when examining Sumerian written traditions. The Sumerian king list describes rulers who supposedly reigned for tens of thousands of years before a great flood transformed the world. Some kings are said to have ruled for 28,800 years, 36,000 years, or even longer. While these figures are clearly not literal human lifespans, scholars remain divided on their meaning. Were they symbolic numbers, astronomical cycles, religious concepts expressed mathematically, or remnants of older traditions whose original significance has been lost? What makes the document especially intriguing is that its later sections begin aligning with rulers and events that can be verified archaeologically, blurring the boundary between myth and history. Perhaps the greatest mystery of all concerns the origins of the Sumerians themselves. Their language does not belong to any known major language family and remains a linguistic isolate. Unlike Indo-European, Semitic, or Sino-Tibetan languages, Sumerian appears to stand alone. This has led to decades of speculation regarding where the Sumerians came from and how their culture developed. Archaeological evidence suggests gradual regional development rather than the arrival of a lost super-civilization, yet significant gaps remain. By the time written history begins, the Sumerians already possessed advanced systems of mathematics, engineering, administration, and urban planning. What do you think is the most fascinating mystery of the Sumerians? Was their advanced knowledge the result of thousands of years of lost development? Or is there still a missing piece of history waiting to be discovered? Share your thoughts in the comments below. In the Judean desert near the Dead Sea, a 5,500-year-old temple stands beside a spring. No palace surrounds it, no city protects it. Yet the people who built it may have possessed engineering knowledge far beyond what archaeologists once thought possible. The site, now known as the Engenuity Chalcolithic Temple, was excavated during the 1960s by archaeologist Benjamin Mazar and his team. Radiocarbon dating placed the sanctuary within the Chalcolithic period, approximately 3,500 to 3,700 BCE. What appeared at first to be a small desert shrine soon became one of the greatest mysteries of prehistoric engineering in the Near East. The first mystery begins with the temple's very existence. Most ancient temples are found within settlements. Egyptian temples stood beside cities, Mesopotamian temples formed the heart of urban centers, and even prehistoric ceremonial sites such as Göbekli Tepe were associated with communities that supported their construction. Engenuity is different. Archaeologists found a carefully planned sanctuary, but no large settlement capable of supporting such a project. The temple consists of a courtyard, stone walls, ceremonial structures, and a distinctive altar, all suggesting organized construction and long-term use. Yet the population center responsible for building and maintaining the complex remains largely unknown. This creates a logistical puzzle. Even a modest temple requires labor, food supplies, planning, transportation of materials, and specialized knowledge. Hundreds of workers may have participated in construction and maintenance over many years. Where did they live? How was labor organized? Who directed the project? More than half a century after excavation began, the answers remain elusive. One of the least discussed but most significant mysteries involves surveying. The temple was not randomly assembled. Its structures follow a coherent plan, walls align with specific spatial relationships, and open areas connect logically to ritual spaces. The sanctuary appears designed rather than gradually accumulated. This is remarkable because the temple predates many of the sophisticated surveying traditions associated with later civilizations. Today, surveyors use laser equipment, GPS systems, and digital mapping. Ancient Egyptian engineers used ropes, measuring rods, and astronomical observations. The builders of En-Gedi had none of these documented tools, yet they successfully established a stable architectural layout within a difficult desert environment. Researchers still debate how Chalcolithic builders measured distances, established straight lines, and maintained consistency during construction. No written manuals survive, and no measuring instruments have been identified with certainty. Whatever methods were used, the knowledge appears to have vanished completely. The location of the temple may reveal another lost technology. En-Gedi is an oasis where fresh water emerges from springs fed by underground geological systems beneath one of the driest regions in the Middle East. The temple was deliberately positioned near this water source. At first glance, this may seem obvious, since human settlements often develop near water, but the precision of the site's placement raises important questions. The builders selected one of the most reliable freshwater locations in the region and understood where water would remain available despite seasonal changes and harsh environmental conditions. Modern hydrogeologists use geological mapping, groundwater modeling, and remote sensing technologies to understand aquifers. How people living more than 5,500 years ago identified and exploited such a favorable location remains uncertain. Some researchers believe generations of environmental observation allowed them to recognize underground water patterns, while others suggest sophisticated local knowledge accumulated over centuries. Whatever the explanation, the builders demonstrated an understanding of landscape resources far beyond simple survival. The temple also presents questions about prehistoric construction methods. Unlike later civilizations that used large-scale masonry blocks, Chalcolithic builders worked with local stone resources. The challenge was not merely obtaining stone, but constructing durable structures capable of surviving harsh desert conditions. Summer temperatures regularly exceed 40 degrees Celsius. Seasonal floods occasionally sweep through nearby valleys, and earthquakes have affected the region throughout history. Despite these challenges, portions of the sanctuary survived for millennia. The builders selected suitable stone, created stable foundations, and developed construction methods that resisted environmental stress. Modern engineers understand how temperature fluctuations create expansion and contraction cycles that gradually weaken structures, yet many elements of the sanctuary endured for more than 5,000 years. This suggests a practical understanding of materials and structural stability that remains difficult to reconstruct today. At the heart of the sanctuary stands one of its most famous features, a crescent-shaped altar. The object immediately stands out because of its unusual form and careful proportions. Creating a symmetrical curved structure without modern drafting tools requires planning, measurement, and geometric understanding. Similar challenges confronted builders at sites such as Stonehenge and Newgrange, where geometry appears embedded within ceremonial architecture. The altar raises fundamental questions. Did the builders possess formal geometric principles? Were proportions transmitted through apprenticeships? Did ritual specialists preserve mathematical knowledge through oral tradition? Because the Chalcolithic culture left no written records explaining its construction methods, archaeologists can only speculate. The altar remains a silent demonstration of knowledge whose origins have been lost. This is the most extraordinary mystery associated with En-Gedi. In 1961, explorers discovered a hidden cache inside a cave near a Nahal Mishmar. approximately 12 kilometers from the temple. The discovery stunned archaeologists. More than 400 artifacts were found carefully wrapped and concealed, including ceremonial staffs, crowns, scepters, standards, mace heads, and complex copper objects unlike anything previously known from the region. The cache became known as the Nahal Mishmar Hoard. Many scholars believe these artifacts may have originated from the En-Gedi temple. If true, the implications are astonishing. The artifacts demonstrate an advanced metallurgical tradition during a period often viewed as technologically primitive. Several objects were produced using lost wax casting, one of the most sophisticated metalworking techniques in human history. Lost wax casting requires creating a wax model, covering it with clay, heating the mold to remove the wax, and pouring molten metal into the cavity. The process demands precise temperature control and extensive technical knowledge, and even minor mistakes can ruin the entire casting. Some Nahal Mishmar artifacts contain extraordinarily complex shapes that would challenge inexperienced metalworkers even today. Researchers have calculated that copper must be heated to approximately 1085 degrees Celsius before melting. Achieving and maintaining such temperatures requires carefully designed furnaces, controlled airflow, high-quality fuel, and skilled operators. This raises a critical question. Where did this knowledge come from? The technology appears surprisingly advanced compared with many contemporary societies. When compared with other Chalcolithic sites throughout the Near East, the craftsmanship of the Nahal Mishmar object stands out dramatically. Some scholars describe the collection as representing one of the earliest known examples of specialized industrial production. The mystery becomes even deeper because the artisans themselves vanished from history. No workshop has been definitively identified, no technical manuals survive, and no written descriptions explain the manufacturing process. Only the artifacts remain. If the hoard truly belonged to the temple, then En-Gedi was not merely a religious center. It may have been part of a technological network capable of producing some of the most sophisticated metal objects on Earth during the 4th millennium BCE. Every ancient monument ultimately leads to the same question: who built it? The society responsible for En-Gedi appears far more organized than earlier models of prehistoric communities suggested. Construction required planning, religious ceremonies required coordination, metallurgical production required specialists, and trade networks supplied raw materials. The copper used in some Chalcolithic artifacts likely originated hundreds of kilometers away, implying long-distance exchange systems operating across large regions of the Near East. Such complexity resembles the organizational capabilities later associated with early states. Yet no king is known, no royal inscriptions exist, and no administrative archives survive. The people responsible remain anonymous. Among the most remarkable prehistoric societies ever discovered, the Cucuteni Tripilia culture flourished across what is now Romania, Moldova, and Ukraine between roughly 5,500 and 2750 BCE. Long before the pyramids of Egypt reached their greatest scale and thousands of years before the rise of classical civilizations such as Greece and Rome, these people created enormous settlements, sophisticated architecture, and some of the most advanced ceramics of the prehistoric world. Yet despite more than a century of archaeological research, many aspects of their technological achievements remain difficult to explain. The greatest mystery is not what they built, but how a society that lacked writing, centralized states, and large-scale metal industries managed to achieve such remarkable levels of organization and craftsmanship. The modern story of the Cucuteni civilization began in 1884 when Romanian archaeologist Teodor Burada discovered unusual pottery fragments near the village of Cucuteni in northeastern Romania. Decades later, additional excavations across Moldova and Ukraine revealed that these artifacts belong to a vast cultural network covering more than 350,000 square kilometers. What initially appeared to be isolated farming communities gradually emerged as one of the largest and most complex Neolithic cultures ever identified in Europe. The real shock came much later. During the late 20th century, aerial surveys, geomagnetic mapping, and satellite-based investigations revealed something archaeologists had never expected to find in a prehistoric farming culture. Beneath fields in central Ukraine were the remains of enormous settlements now known as megasites. Locations such as Talyanki, Maidanetske, and Dobrovody covered between 250 and 450 hectares. Some estimates suggest populations ranging from 10,000 to 15,000 inhabitants, while a few models propose numbers approaching 20,000. To understand how extraordinary this is, one must compare these settlements with other societies of the same era. Around 4000 BCE, many communities across Europe consisted of only a few dozen households. Even some of the earliest urban centers of Mesopotamia would not reach comparable scales until centuries later. Yet, somehow, the people of Cucuteni Tripilia gathered thousands of individuals into organized settlements without evidence for kings, palaces, armies, or bureaucratic administrations. The layout of these settlements presents another puzzle. Archaeological surveys reveal houses arranged in concentric circles extending outward from large central open spaces. In some cases, more than 2,000 structures were organized into remarkably consistent geometric patterns. Modern researchers can easily recognize these layouts through computer-generated maps, but the question remains, how were they designed in the first place? There is no evidence that the inhabitants possessed written plans, advanced surveying instruments, or mathematical systems comparable to those used by later civilizations. Nevertheless, entire communities appear to have followed a common architectural vision across areas covering hundreds of hectares. Some scholars suspect the existence of standardized measurement systems that have left no direct trace in the archaeological record. Yet among all Cucuteni mysteries, nothing fascinates researchers more than their ceramics. The pottery produced by this culture is often regarded as some of the finest ever created during the Neolithic period. Even today, museum visitors are frequently surprised to learn that these vessels were manufactured thousands of years before the invention of the potter's wheel became widespread in Europe. The surfaces of bowls, jars, and ritual vessels are covered with complex spirals, flowing curves, nested geometric motifs, and intricate painted patterns that display extraordinary symmetry. At first glance, these decorations appear artistic. Under closer examination, however, they reveal a technological mystery. Producing such precision consistently across a territory spanning hundreds of thousands of square kilometers required a degree of technical control rarely associated with Stone Age societies. Many vessels feature nearly identical proportions, balanced compositions, and carefully repeated motifs. Experimental archaeologists attempting to recreate these objects have discovered that achieving the same visual consistency demands extensive experience and precise control over materials and firing conditions. Scientific analysis has shown that Cucuteni potters carefully selected specific clay mixtures, often removing impurities before shaping their vessels. Mineralogical studies indicate that firing temperatures commonly reach between 800 and 1000 degrees Celsius. For comparison, many earlier Neolithic cultures typically operated at lower and less stable temperatures. Maintaining such conditions is difficult even with modern reconstructions of ancient kilns. Temperature fluctuations can cause cracking, warping, or color inconsistencies. Yet thousands of Cucuteni vessels display remarkably uniform results. Even more intriguing is their mastery of color technology. The characteristic red, black, and white palette found on many Cucuteni ceramics required a sophisticated understanding of chemical transformations during firing. The final colors depended not only on pigments, but also on oxygen levels inside the kiln. Modern ceramic engineers understand how oxidation and reduction atmospheres influence mineral reactions, but it remains unclear how prehistoric potters acquired enough practical knowledge to control these processes so effectively. No written manuals existed. No technical diagram survived. Nevertheless, generations of artisans repeatedly produced ceramics with predictable outcomes. Researchers have also been puzzled by the apparent simplicity of the kilns themselves. Excavated firing structures are relatively modest compared with the technological sophistication of the finished products. This creates an apparent contradiction. How could simple installations generate such reliable results? Some specialists suggest that the true expertise was not embedded in the kiln design, but in operational techniques passed down through oral traditions. If so, an enormous body of practical engineering knowledge vanished without leaving direct evidence behind. The scale of ceramic production presents another challenge. Thousands upon thousands of vessels have been recovered from Cucuteni sites. Such quantities imply specialized production systems and extensive knowledge transfer across large regions. Yet unlike later civilizations, there's little evidence for centralized workshops controlling standards. Somehow, communities separated by hundreds of kilometers maintained remarkably similar artistic and technical traditions over centuries. The mechanism behind this cultural consistency remains poorly understood. Architecture provides additional evidence of unexpected technological sophistication. Excavations reveal that many Cucuteni houses were not simple huts, but substantial structures with wooden frames, clay walls, elevated floors, and sometimes second stories. Reconstructions suggest heights exceeding 6 meters in certain cases. Building multi-level structures requires an understanding of load distribution and structural stability. Although prehistoric builders certainly relied on experience rather than formal engineering equations, their success indicates practical knowledge accumulated over generations. One of the strangest mysteries involves fire. Archaeologists have discovered that many Cucuteni settlements were intentionally burned. In some locations, temperatures appear to have exceeded 1,000 degrees Celsius, transforming clay walls into hardened ceramic-like material. The phenomenon is so widespread that it cannot easily be dismissed as accidental destruction. Some researchers argue that houses were deliberately burned as part of ritual practices. Others propose social or symbolic explanations linked to community renewal. Regardless of the motive, generating such temperatures repeatedly would have required large quantities of fuel and careful management of combustion processes. Once again, the evidence points toward technological capabilities that seem surprisingly advanced for the period. Trade networks further complicate the picture. Raw materials found at Cucuteni sites often originated hundreds of kilometers away. Flint, copper, salt, and specialized clays moved through extensive exchange systems connecting distant communities. Such networks suggest sophisticated logistical organization despite the apparent absence of centralized political authority. How these systems functioned across such vast territory remains one of the most debated questions in European prehistory. One of the greatest mysteries of the Cucuteni Tripilia culture is that it displayed many features of a civilization without the institutions usually associated with one. There were no palaces, monumental temples, dynastic rulers, or written records, yet large populations organized construction, maintained trade networks, and developed impressive technologies and artistic traditions. Ponagar Cham Towers is a 1,000-year-old temple complex overlooking the coast of Nha Trang in central Vietnam. More than a religious monument, it is one of Southeast Asia's greatest engineering mysteries. The towers have survived tropical storms, humidity, salt-laden sea air, and centuries of weathering. Yet many of the construction techniques behind them remain only partially understood. The mystery begins with the bricks. The towers have been known locally for centuries and were documented by European travelers and scholars during the 19th century. Archaeological investigations throughout the 20th century reveal that the surviving structures were built primarily between the 8th and 13th centuries by the Cham civilization, one of the most advanced maritime cultures in Southeast Asia. What researchers expected to find was a typical medieval brick monument. What they found instead was a technological puzzle that remains unsolved. One of the first things visitors notice at Ponagar is the unusual appearance of the brick walls. Unlike many ancient structures where mortar joints are clearly visible, the bricks at Ponagar seem almost fused together. In some sections, the joints are so thin that they are difficult to detect even at close range. For more than a century, archaeologists, engineers, and materials scientists have debated a simple question. How were these bricks joined? Several theories have been proposed. One theory suggests that the Cham builders used an organic adhesive derived from local plant resins. Another proposes that an extremely thin mineral-based mortar was applied and later became nearly indistinguishable from the bricks themselves. A third theory suggests that the bricks may have been partially bonded through heating processes after construction. None of these explanations fully account for all observed evidence. Laboratory analyses have detected traces of organic compounds on some brick surfaces, but no single substance has been identified that could explain the remarkable durability of the joints over 1,000 years. The puzzle becomes even more interesting when Ponagar is compared with other Cham monuments such as Mai Sun and Poklong Garai. The same construction characteristics appear repeatedly across hundreds of kilometers, suggesting that the builders possessed a standardized technology whose details have largely disappeared from history. Perhaps the most fascinating mystery at Ponagar concerns the bricks themselves. Modern materials analysis has shown that Cham bricks differ significantly from many contemporary building materials used elsewhere in Southeast Asia during the same period. The bricks display exceptional uniformity, their density is relatively consistent, their porosity appears carefully controlled, and their ability to absorb and release moisture is unusually effective. These characteristics are important because tropical environments are among the most destructive settings for ancient architecture. Moisture enters building materials, expands during temperature changes, promotes biological growth, and gradually weakens structures. Yet many of the bricks at Ponagar have survived for more than a millennium. Researchers studying the material have noted that the bricks possess a balance between strength and permeability. Rather than completely resisting moisture, they allow water vapor to move through the structure, reducing internal stress and preventing large-scale cracking. This principle resembles concepts employed in some modern conservation materials. The question is how medieval Cham craftsmen achieved such results. Producing high-quality bricks requires control over several variables simultaneously: clay selection, mineral composition, particle size, water content, drying conditions, firing temperature, firing duration, and cooling rate. Even small variations can dramatically affect the final product. Modern industrial brick production relies on laboratory testing, temperature sensors, and precisely controlled kilns. The Cham builders possessed none of these technologies, yet the final results remain impressive. Some materials scientists estimate that firing temperatures may have exceeded 800 to 900 degrees Celsius, while remaining sufficiently controlled to avoid excessive deformation or cracking. The challenge becomes even greater when considering scale. The main tower alone rises more than 20 meters above the ground. Combined with the surrounding structures, the complex required hundreds of thousands of bricks. This raises another mystery. Where were the production facilities? Archaeologists have not discovered kiln complexes large enough to explain the enormous quantity of material used in major Cham construction projects. If massive industrial-scale brick production existed, much of the evidence has either disappeared or remains undiscovered. Comparisons with other ancient civilizations make the achievement even more remarkable. Roman builders became famous for concrete. The Maya mastered limestone construction. The Khmer Empire developed sophisticated sandstone architecture at Angkor. The Cham civilization appears to have specialized in advanced fired brick technology, yet unlike Roman concrete, whose composition can be studied directly, crucial aspects of Cham brick production remain uncertain. Ponagar stands only a short distance from the sea. Marine environments are notoriously destructive. Salt carried by wind penetrates building materials and accelerates deterioration. Tropical storms generate extreme rainfall and powerful winds. High humidity encourages biological growth. Many modern reinforced concrete structures require significant maintenance under similar conditions. Yet Ponagar has remained standing for centuries. Engineers studying the towers have identified several features that may have contributed to their longevity. The walls are exceptionally thick. The towers taper gradually toward the top. Weight is distributed vertically through massive structural cores, and openings are limited and strategically positioned. Together, these characteristics create a highly stable structure capable of resisting environmental stress. The design demonstrates an understanding of load distribution that appears remarkably sophisticated for the period. Although the towers are primarily constructed from brick, important architectural and religious elements were carved from stone. The most famous example is the statue of the goddess Yan Po Nagar, originally one of the most significant sacred objects in the complex. Some stone components weigh several tons. Transporting such materials presented major logistical challenges. The Cham builders had no cranes, hydraulic lifts, or modern transportation systems, yet they successfully integrated heavy stone elements into elevated architectural settings. How they accomplished this remains uncertain. Researchers generally assume the use of ramps, rollers, ropes, and coordinated labor forces, but direct archaeological evidence is limited. The problem resembles questions asked at Borobudur in Indonesia and Angkor Wat in Cambodia. The monuments survive. The precise construction procedures remain largely unknown. One of the most remarkable aspects of Ponagar is simply that it still exists. More than 1,000 years of environmental exposure should have produced far greater damage. Instead, the towers continue to dominate the landscape. Their survival suggests that Cham builders understood principles of structural stability through generations of accumulated experience. Without formal engineering equations, computer simulations, or modern mathematics, they developed architectural solutions that proved effective over centuries. This knowledge was likely transmitted through apprenticeships and practical training. Unfortunately, very little written technical documentation survives. The buildings remain, the engineering manuals do not. Across the rolling hills of central Italy, between the Arno and Tiber rivers, a remarkable civilization emerged more than 2,800 years ago, with engineering expertise, advanced metalworking techniques, and urban planning skills that appeared far ahead of their time. Long before Rome rose to imperial power, the Etruscans were constructing stone cities, draining marshlands, carving roads through solid rock, and creating finely crafted metal artifacts whose sophistication continues to impress historians and archaeologists today. The modern rediscovery of the Etruscans happened gradually rather than through a single dramatic excavation. During the Renaissance, unusual tombs filled with painted walls and luxury artifacts began appearing beneath Italian farmland. By the 18th and 19th centuries, systematic excavations at sites such as Tarquinia, Cerveteri, Veii and Vulci revealed an entire lost civilization. Archaeologists uncovered thousands of tombs, bronze statues, jewelry, inscriptions, roads, and city walls. Yet despite more than 2 centuries of research, one fundamental question remains unanswered. Who exactly were the Etruscans, and how did they acquire technological knowledge that often appears unexpectedly advanced for its time? The mystery begins with their language. More than 13,000 Etruscan inscriptions have been discovered. Scholars can read the letters because the alphabet is related to Greek writing, yet most of the language itself remains only partially understood. This creates an unusual situation in archaeology. Researchers can pronounce many words but often cannot fully understand what they mean. Entire sections of Etruscan knowledge may therefore remain hidden in texts that survive physically but remain intellectually inaccessible. It is as if a technical manual from an advanced society existed, but nobody could completely translate it. Among the most remarkable achievements of the Etruscans was their ability to transform landscapes through hydraulic engineering. Large areas of central Italy consisted of marshes, flood-prone valleys, and difficult terrain. Archaeological evidence shows that Etruscan engineers constructed extensive drainage networks, artificial channels, reservoirs, and underground tunnels to manage water. Some tunnels were excavated through volcanic rock and extended for hundreds of meters. Even more impressive, several were dug from opposite directions and met with astonishing accuracy in the middle. Modern engineers accomplish similar tasks using surveying instruments, laser measurements, GPS systems, and detailed mapping. The Etruscans possessed none of these technologies, yet many of their hydraulic works continued functioning for centuries. Some systems later became foundations for Roman infrastructure, suggesting that Rome inherited engineering knowledge rather than inventing it independently. Yet no Etruscan achievement generates more fascination than their extraordinary mastery of metalworking. The civilization controlled rich mineral deposits throughout central Italy, particularly on Elba Island, where vast iron ore reserves supplied ancient industries. Archaeological studies estimate that thousands of tons of ore were extracted and processed during the height of Etruscan power between the 7th and 5th centuries BCE. Ancient slag deposits found across Tuscany indicate large-scale industrial production unprecedented in much of contemporary Europe. The scale alone is impressive, but the true mystery lies in the quality of their work. Etruscan craftsmen produced weapons, armor, mirrors, ceremonial objects, sculptures, and jewelry, displaying levels of precision that challenge assumptions about ancient technology. Metallurgical analysis has revealed carefully controlled alloy compositions, suggesting detailed practical knowledge of temperatures, ore selection, and material behavior. Some bronze artifacts contain highly consistent mixtures of copper and tin, while certain iron objects display properties indicating sophisticated forging techniques. Perhaps the most astonishing examples are their gold ornaments. Etruscan jewelers perfected a process known as granulation, in which microscopic gold spheres are attached to a surface to create intricate decorative patterns. Many surviving pieces contain thousands of tiny gold beads, some measuring less than 0.2 millimeters in diameter. Under magnification, these decorations appear almost machine-made. The precision rivals work produced by highly specialized craftsmen using modern tools. The mystery is not simply that the Etruscans created such objects, the mystery is how they created them. Modern researchers have spent decades attempting to reconstruct the granulation process. Experimental archaeologists can reproduce similar results today, but often only with carefully controlled laboratory conditions, magnification equipment, and modern metallurgical knowledge. Ancient craftsmen achieved comparable outcomes more than 2,500 years ago. Even more puzzling, many Etruscan gold artifacts show little evidence of conventional soldering. Traditional methods would leave traces indicating where separate components were joined together. In numerous cases, those traces are either extremely subtle or entirely absent. Some researchers propose that the Etruscans employed advanced diffusion bonding techniques involving organic compounds and precise heating conditions. Others argue that lost chemical processes may have been used. No consensus exists. The exact procedures that allowed Etruscan artisans to attach thousands of microscopic gold spheres remain one of the most enduring technological mysteries of the ancient Mediterranean. The sophistication of Etruscan metallurgy becomes even more striking when compared with neighbouring cultures. During the same period, many European societies were still transitioning between Bronze Age and Iron Age technologies, yet Etruscan workshops were already producing luxury metalwork traded throughout the Mediterranean. Their products have been found hundreds of kilometres from their homeland, demonstrating participation in extensive commercial networks linking Italy with Greece, Phoenicia, North Africa, and beyond. Such trade required not only craftsmanship but also advanced systems of resource extraction, transportation, and economic organization. Their engineering abilities extended beyond metal. Massive stone walls surrounding Etruscan cities were constructed, using blocks weighing several tons. Some gateways employed true arches long before Roman architecture popularized them across Europe. Structures such as the famous gates of Perugia and Volterra demonstrate an understanding of load distribution that would influence later Roman construction. The question is not whether the Romans improved these techniques, they undoubtedly did, but how much of Rome's architectural success originated with the civilization it eventually absorbed. Underground architecture presents another mystery. At sites such as Cerveteri, entire necropolises were carved into rock, creating underground cities for the dead. Streets, chambers, doorways, columns, benches, and architectural details were sculpted directly from stone. Thousands of tons of material had to be removed with remarkable precision, yet few records explain the tools, planning methods, or labor systems required to complete projects on such a scale. Astronomy may also have played a role in Etruscan engineering. Several cities, temples, and sacred spaces appear aligned with celestial events. Certain structures correspond to solar positions during significant times of the year. Similar alignments are known from Egypt, Mesopotamia, and Mesoamerica, but the mathematical methods used by Etruscan planners remain uncertain because so much of their written knowledge remains undeciphered. The Etruscans didn't vanish suddenly. Between the 4th and 1st centuries BCE, they were gradually absorbed by the growing Roman Republic. Their language and independence disappeared, but their influence remained. Roman engineering, urban planning, religion, and architecture were all shaped by Etruscan knowledge. St. Simeon Monastery stands on the west bank of the Nile near Aswan in southern Egypt. The massive complex was first documented by European travellers during the 19th century and later examined by archaeologists studying the development of early Christian communities in Egypt. Built between the 7th and 10th centuries CE and abandoned around the 13th century, the monastery remains one of the largest surviving desert monastic settlements ever discovered in North Africa. At first glance, it appears to be little more than a ruined religious complex, yet closer examination reveals something far more intriguing: a self-sustaining fortress city constructed in one of the harshest environments on Earth. The mystery is not why monks lived here. The mystery is how they managed to survive here at all. The greatest mystery of St. Simeon begins with a simple question. Where did the water come from? The monastery sits on elevated ground overlooking the Nile. This location provided strategic advantages, including visibility and protection from flooding, but it created a severe logistical problem. Every litre of water needed for drinking, cooking, washing, agriculture, and animals had to be transported uphill. Archaeological surveys have revealed large cisterns, storage basins, channels, and collection systems integrated throughout the complex. These installations indicate sophisticated water management rather than simple manual transport. Scientists estimate that an average person living in an arid environment requires at least several litres of water daily for survival. If St. Simeon housed between 300 and 1,000 residents, annual consumption could have reached millions of litres. The challenge becomes even more remarkable when considering Aswan's climate. Modern rainfall averages only a few millimetres per year, meaning water harvesting alone could not have sustained such a population. Some researchers suggest that caravans and animal transport systems carried water from the Nile, while others argue that a highly organised supply infrastructure connected the monastery to river-based distribution networks. Yet no complete blueprint of the system survives, and the exact mechanism that sustained hundreds of people for centuries remains one of the monastery's greatest unsolved engineering puzzles. Religious communities generally build places of worship, but St. Simeon built defensive walls. The monastery is surrounded by massive fortifications reaching approximately 10 meters in height, and the outer walls resemble military architecture more than traditional religious construction. Why would monks require defenses on such a scale? The answer may lie in the monastery's location along important trade routes linking Egypt with Nubia and regions farther south. Historical records indicate periods of political instability, tribal conflict, and raids across the region. Yet the engineering itself remains remarkable. The builders used mud bricks reinforced through techniques that allowed the walls to withstand centuries of erosion, temperature fluctuations, and desert winds. Even after hundreds of years of abandonment, significant sections remain standing. Modern engineers understand how difficult it is to preserve earthen architecture, and many contemporary mud brick structures deteriorate rapidly without maintenance. St. Simeon's walls survived nearly a millennium, yet the exact construction methods, material mixtures, and maintenance procedures employed by the builders remain only partially understood. Most large settlements are built on relatively flat terrain, but St. Simeon was not. The monastery occupies a steep desert hillside where elevation changes create major architectural challenges. Instead of leveling the landscape, the builders designed a complex system of terraces, stairways, courtyards, storage chambers, workshops, and residential quarters integrated directly into the terrain. This required advanced planning. Every wall had to account for slope stability, every foundation had to support structures above and below it, and every pathway had to connect different sections efficiently while allowing movement of people, animals, food, and construction materials. Modern archaeological mapping reveals a carefully organized layout rather than random expansion. The design resembles some Byzantine fortified settlements and certain mountain monasteries found throughout the eastern Mediterranean. However, no written construction manuals from St. Simeon have survived. As a result, researchers can observe the engineering solution but cannot fully reconstruct the design process behind it. Water was not the only challenge. Food represented an equally complex problem. Excavations have uncovered granaries, storage facilities, kitchens, animal enclosures, and work areas distributed throughout the monastery. These discoveries indicate that St. Simeon functioned as a large economic centre rather than a simple place of worship. To sustain hundreds of residents, enormous quantities of grain, vegetables, oil, and livestock products would have been required. Archaeologists estimate that a community of several hundred people could consume dozens of tons of food annually. The surrounding desert provided little agricultural potential, so supplies had to arrive continuously from the Nile Valley or associated trade networks. This raises another question. How did the monastery coordinate transportation, storage, preservation, and distribution of resources across centuries? The organizational complexity begins to resemble that of a small medieval city, yet much of the administrative system responsible for this achievement has disappeared from history. One of the most overlooked mysteries involves the monastery's construction materials. Many visitors assume the walls are simple mud bricks, but scientific studies suggest otherwise. Ancient builders often modified mud brick mixtures using combinations of clay, sand, straw, organic fibers, and mineral additives. These ingredients could dramatically affect durability, insulation, and resistance to cracking. St. Simeon exists within an environment where daytime temperatures can exceed 40 degrees Celsius, while nighttime temperatures drop significantly. Such thermal stress normally causes rapid deterioration, yet portions of the monastery have survived for nearly 1,000 years. Researchers continue to analyze surviving brick samples to understand how their composition contributed to long-term stability. Some results suggest an impressive understanding of local materials and environmental adaptation. The builders may not have possessed modern chemistry, but they clearly understood practical material science. Exactly how much knowledge they possessed remains uncertain. For centuries, historians imagined desert monasteries as isolated communities, but St. Simeon tells a different story. Excavations have uncovered imported ceramics, foreign goods, and evidence of commercial interaction extending beyond the immediate region. Its position near major Nile and caravan routes likely transformed the monastery into an important waypoint, connecting Egypt with Nubia and sub-Saharan trade networks. Ideas traveled alongside merchants, and technologies traveled alongside ideas. Construction techniques, agricultural practices, storage methods, and engineering knowledge could have moved across enormous distances through these networks. The monastery may have functioned not only as a religious center, but also as a hub for technological exchange. Yet the exact routes through which knowledge reached St. Simeon remain poorly understood. The archaeological evidence reveals the connections, but the historical details remain frustratingly incomplete. Wemyss Caves is a place where an entire lost language may have been carved into stone. Cut into the sandstone cliffs of the Fife Coast in eastern Scotland, overlooking the Firth of Forth, these sea caves contain one of the largest concentrations of ancient Pictish carvings ever discovered. More than 8,000 individual markings have been documented across the cave system, ranging from mysterious symbols and human figures to animals, ships, crosses, and inscriptions spanning over 1,000 years of history. Yet despite decades of archaeological investigation, the greatest mystery of Wemyss Caves is not what the carvings depict. It is how the people who created them achieved such remarkable geometric precision, symmetry, and durability in one of the harshest coastal environments in northern Europe. The caves were never truly lost. Local communities had known about them for centuries. However, their archaeological importance began attracting serious attention during the 19th century, when antiquarians recorded unusual carvings on the cave walls. Systematic surveys throughout the 20th century revealed that Wemyss contained the highest concentration of Pictish cave carvings known anywhere in Britain. Modern laser scanning and digital recording projects conducted during the 21st century dramatically expanded the catalogue of known symbols, uncovering details that had become almost invisible to the human eye through centuries of erosion. The Picts themselves remain one of the most enigmatic peoples in European history. Occupying much of northern and eastern Scotland during the Late Iron Age and early medieval period, they left behind impressive symbol stones, fortified settlements, metalwork, and monumental architecture. Yet unlike the Romans, Greeks, or Anglo-Saxons, they left almost no written records that can explain their beliefs, social structures, or symbolic systems. As a result, every Pictish carving discovered today becomes a fragment of a puzzle that scholars still cannot fully reconstruct. The first mystery begins with the environment itself. Wemyss caves sit directly beside the North Sea. The sandstone cliffs are constantly exposed to salt spray, moisture, temperature fluctuations, and powerful coastal storms. Modern geological studies demonstrate that sandstone in such environments experiences continual granular disintegration. Individual mineral grains gradually loosen and detach from the rock surface. Over centuries, even deep carvings can become distorted beyond recognition. Yet, many of the Pictish symbols at Wemyss remain surprisingly identifiable despite having been exposed to these conditions for well over a millennium. This preservation creates a technological question. Did the carvers deliberately select specific rock surfaces that were more resistant to weathering? Geological surveys show that sandstone layers within the caves vary considerably in hardness, grain size, and cementation. Some sections deteriorate rapidly while others remain relatively stable. Several of the most important carvings appear to occupy precisely those areas where erosion has been slower. If this pattern is intentional rather than accidental, it suggests practical geological knowledge rarely associated with early medieval societies. Even more intriguing is the extraordinary precision of the carvings themselves. Among the most famous symbols found at Wemyss are the double disc, the crescent and V-rod, and the mirror symbols. At first glance, these designs appear simple. However, closer analysis reveals levels of geometric control that continue to surprise researchers. Many of the symbols display balanced proportions, carefully controlled curves, and symmetrical relationships that remain consistent despite being carved into uneven natural rock surfaces. The double disc symbol provides one of the most striking examples. Two circles of nearly identical diameter are connected by a decorated bar. Reproducing such a design freehand on rough sandstone would be difficult even for a skilled modern artist. Yet multiple examples throughout Pictish Scotland exhibit remarkably similar proportions. This consistency raises a fundamental question. How were these shapes planned? No measuring tools associated with Pictish carving have ever been discovered. There is no archaeological evidence for specialized compasses, drafting instruments, or geometric templates. Nevertheless, digital analysis of surviving carvings suggests that many symbols deviate only slightly from ideal geometric forms. Some researchers have proposed the use of chords, wooden guides, or simple proportional systems. Others suggest experienced artisans may have learned standardized construction methods through generations of apprenticeship. The problem is that no direct evidence survives to confirm any of these theories. The challenge becomes even greater when one considers the physical conditions under which the carvings were created. Unlike the smooth marble surfaces used by Greek sculptors or the prepared limestone blocks used by Egyptian artisans, the walls of Wemyss caves are naturally irregular. Cracks, ridges, and varying textures distort visual perception. Achieving balanced symmetry on such surfaces requires not only artistic skill, but also advanced spatial judgment. Modern experimental archaeology has demonstrated that reproducing some Pictish symbols on uneven stone often requires repeated measurement and correction. Yet the original carvings show surprisingly few signs of major adjustments. Comparisons with other ancient symbolic traditions make the mystery even more remarkable. Scandinavian rock carvings from the Bronze Age frequently emphasize figures and scenes, but rarely demonstrate the same degree of abstract geometric standardization. Celtic art developed complex curvilinear patterns, yet many examples date centuries later than the earliest Pictish symbols. Roman military inscriptions exhibit precision because they relied upon established engineering traditions and written standards. The Picts appear to have achieved comparable consistency without leaving behind any equivalent technical documentation. The possibility that these symbols formed part of a larger information system introduces another layer of complexity. More than 40 recurring symbol types are known across Pictish Scotland. Many appear in repeated combinations. Certain pairings occur so consistently that some scholars believe they may represent names, lineages, territorial markers, or administrative identities. Statistical studies have shown that the symbols do not occur randomly. Their distribution resembles structured communication systems more closely than decorative art. If the symbols functioned as information carriers, precision suddenly becomes far more important. A slight variation in shape could alter meaning, much as changing a letter can alter a word. This possibility may explain why geometric consistency appears across sites separated by hundreds of kilometers. Wemyss caves may therefore preserve evidence not merely of artistic expression, but of a symbolic language whose rules remain unknown. Another mystery involves the decision to place these carvings inside caves rather than on exposed standing stones. Throughout Scotland, Pictish symbols commonly appear on monumental stones, erected in visible public locations. Wemyss presents a different pattern. Here, many carvings are hidden within dark coastal chambers, accessible only through narrow entrances. Such locations seem poorly suited for public communication. One explanation suggests ritual use. Across many ancient cultures, caves were viewed as liminal spaces positioned between worlds. Archaeological examples range from Paleolithic painted caves in France and Spain to sacred caverns in the Mediterranean. The acoustics of Wemyss strengthen this possibility. Several caves produce unusual resonance effects when waves strike the entrances. Sound reflections can amplify low frequencies and create prolonged echoes. Modern acoustic measurements indicate that certain chambers naturally generate reverberation patterns capable of altering human perception of space. If the Picts deliberately selected caves with distinctive acoustic properties, they may have understood environmental effects that modern researchers are only beginning to quantify. Similar discussions have emerged regarding prehistoric monuments such as Stonehenge, Newgrange, and several megalithic tombs, where acoustics appear unusually significant. While no direct evidence proves intentional acoustic engineering at Wemyss, the correlation remains difficult to ignore. The carvings also reveal evidence of long-term cultural continuity. Some caves contain artwork spanning multiple centuries. Early Pictish symbols coexist with later Christian crosses, medieval inscriptions, and post-medieval markings. This suggests that specific caves retained importance across generations, despite major political and religious changes. Maintaining such continuity would have required transmission of cultural knowledge over long periods. Yet the mechanisms by which that knowledge survived remain largely invisible in the archaeological record. Nestled in the mountains of southern Uzbekistan near the border with Tajikistan, Uzundara Fortress stands as one of the most remarkable surviving military strongholds of the Greco-Bactrian kingdom. Archaeological excavations that began in the early 2010 era revealed a remarkably well-preserved site dating to approximately the 3rd–2nd centuries BCE. Positioned high above a narrow mountain corridor, the fortress controlled one of the most strategic routes into ancient Bactria. Yet more than 2,000 years later, many of the engineering secrets behind its construction and operation remain unexplained. The first mystery begins with geography. Modern satellite analysis shows that Uzundara occupies an exceptionally advantageous location. The fortress overlooks a narrow mountain pass that naturally funnels movement through the region. Any army attempting to enter Bactria from the north would have been forced through this corridor, placing it directly under observation. What puzzles researchers is how ancient engineers identified such an ideal position without modern surveying equipment. Today, military planners use topographic mapping, aerial reconnaissance, satellite imagery, and computer simulations to evaluate defensive positions. Yet the builders of Uzundara possessed none of these technologies. Even so, they selected a location that military historians describe as remarkably efficient. The fortress commands extensive views across surrounding valleys while minimizing vulnerable approaches. Similar strategic positioning can be observed at Hellenistic fortifications in Afghanistan and parts of the former Seleucid Empire, but Uzundara stands out because of the complexity of its mountainous terrain. Some archaeologists believe generations of accumulated geographic knowledge may explain the choice, while others argue that Greek military surveyors developed practical methods capable of analyzing landscapes with surprising precision. Whatever the explanation, the decision demonstrates an understanding of terrain that rivals many later military systems. One of the most surprising discoveries concerns the scale of the defences. Excavations have revealed massive walls reinforced with numerous towers, carefully planned firing positions, and defensive arrangements capable of covering multiple attack routes simultaneously. Archaeologists have recovered thousands of arrowheads from the site, suggesting the fortress was heavily militarized. The mystery is that the defensive capacity appears unusually large for a remote frontier outpost. Military calculations indicate that a relatively modest garrison could effectively control the mountain pass, yet the fortress was built as though its designers expected sustained assaults by significant enemy forces. This naturally raises the question: who were these enemies? The Greco-Bactrian kingdom faced pressure from nomadic groups across Central Asia, including tribes originating from the Eurasian steppe. Historical records describe migrations and invasions occurring throughout the region during the centuries following Alexander the Great's campaigns. Some scholars suggest Uzundara may have formed part of a larger defensive system, protecting Bactria from these threats, while others believe the fortress defended economically important trade routes that connected Central Asia with emerging Silk Road networks. The true scale of the danger that inspired such extensive defences remains unknown. Perhaps the most fascinating engineering mystery concerns logistics. Military historians often emphasize that armies march on food, water, and supplies rather than weapons alone. Building a fortress is difficult, but keeping it operational for years is far more challenging. Uzundara stands hundreds of meters above surrounding valleys in rugged terrain, meaning every stone block, every weapon, every storage jar, and every food supply had to reach the site somehow. Excavations uncovered evidence of long-term occupation, including storage facilities, military equipment, and domestic artifacts. These findings indicate that soldiers lived and worked here continuously rather than occupying the fortress only during emergencies. This raises difficult questions about how much food was required annually, where water was obtained during dry seasons, and how construction materials were transported uphill. Modern military studies show that maintaining a mountain outpost often requires several times more logistical effort than supporting forces on flat terrain, and similar challenges confronted Roman garrisons in alpine regions centuries later. Yet the Greco-Bactrian kingdom managed to maintain Uzundara long before the development of many sophisticated logistical systems associated with Rome. The exact supply network remains largely invisible in the archaeological record. Uzundara lies more than 3,000 kilometers from Greece. Despite this enormous distance, many architectural features display unmistakable influences from Hellenistic military engineering traditions. The fortress demonstrates sophisticated planning, with towers positioned to maximize visibility and defensive coverage, wall segments exploiting natural rock formations, and defensive zones overlapping in ways that increased battlefield effectiveness. This raises a significant question. How did advanced engineering knowledge travel so far from the Mediterranean world? The campaigns of Alexander the Great spread Greek culture across vast territories, but maintaining technical expertise over such distances presented enormous challenges. Engineers, architects, military officers, and craftsmen would have needed to transfer specialized knowledge across generations. Some historians compare this process to the spread of Roman engineering throughout Europe centuries later, while others argue that local Central Asian traditions merged with imported Greek techniques, producing hybrid forms of military architecture unique to the region. Exactly how this knowledge was transmitted remains uncertain. No fortress operates in isolation. Researchers increasingly suspect that Uzundara formed part of a larger chain of military observation posts scattered across the frontier. If correct, this network would have allowed warnings to travel rapidly across great distances. The concept is not unprecedented. The Romans later developed extensive signaling systems along their borders. Ancient China employed beacon towers capable of transmitting alerts across hundreds of kilometers, and similar systems existed in the Byzantine and Islamic worlds. However, evidence suggests Uzundara may represent an earlier example of such frontier communication. The fortress occupies a position with exceptional visibility, and several nearby elevated locations could potentially have functioned as relay stations. Yet major questions remain unanswered. What signals were used? Smoke, fire, or reflective surfaces? How quickly could information travel? Could an invasion be reported within hours rather than days? Until additional sites are excavated, the communication system remains largely hypothetical. The mountains surrounding Uzundara present environmental challenges beyond warfare. Strong winds, seasonal temperature fluctuations, erosion, and seismic activity all threaten long-term structures, yet significant portions of the fortress survived for more than 2 millennia. Archaeologists have noted that many sections of the fortress incorporate natural bedrock directly into defensive structures. Rather than forcing the landscape to conform to a predetermined design, the engineers adapted their construction to existing geological features. This strategy reduced the amount of material required while increasing structural stability. Modern engineers often employ similar principles when designing infrastructure in mountainous regions. By integrating natural formations into construction plans, they reduce stress on artificial structures and improve resistance to environmental forces. The extent to which ancient builders consciously understood these principles remains debated, but the results nevertheless demonstrate remarkable practical knowledge. The final mystery concerns the fortress's disappearance. Archaeological evidence suggests that Uzundara was eventually abandoned during a period of regional instability associated with nomadic incursions and the decline of Greco-Bactrian power. Yet the abandonment appears surprisingly rapid. Many frontier fortifications throughout history evolve gradually, changing functions as political conditions shift. But Uzundara seems to have experienced a more abrupt fate. After centuries of development, the knowledge required to design, supply, and operate such a sophisticated mountain fortress largely vanished from the region. This pattern appears repeatedly throughout history. The engineers who built Roman aqueducts disappeared. the specialists responsible for constructing massive Egyptian monuments vanished, and the craftsmen who created the Antikythera mechanism left behind almost no written explanation of their techniques. Usundara presents a similar puzzle. The walls survive, the towers survive, and the artifacts survive, but the people who understood how the entire system functioned have disappeared from history. Jarlshof is a windswept archaeological settlement standing on the southern tip of mainland Shetland, Scotland, where the North Sea and the Atlantic Ocean collide. Few places on Earth preserve such an extraordinary record of human occupation. Within a single site, archaeologists have uncovered evidence spanning more than 4,000 years, from the Late Bronze Age around 1200 BC through the Iron Age, the Pictish period, the Viking Age, and into the medieval era. What makes Jarlshof remarkable is not merely its age, but the technological questions hidden within its layers. Across 40 centuries, different societies repeatedly chose the same location, built increasingly sophisticated structures, maintained long-distance trade networks across some of the world's most dangerous seas, and developed engineering solutions that continue to surprise researchers today. The site was discovered almost by accident. During the winter storms of the 1890s, powerful waves eroded part of the coastline near Sunbury Head and exposed buried stone walls beneath the turf. The remains attracted the attention of scholars, and systematic excavations led by archaeologist Alexander Curl between 1925 and 1935 revealed an archaeological sequence unlike anything previously found in Britain. Layer after layer emerged from the ground. Instead of a single settlement, investigators found an entire timeline of human civilization stacked one upon another. Every generation appeared to have inherited the location, modified it, and left behind clues to its technological capabilities. One of the first mysteries concerns the site's astonishing continuity. Most ancient settlements were eventually abandoned because of climate change, resource depletion, warfare, or environmental deterioration. Jarlshof somehow remained attractive for more than 4 millennia. The question is why? Shetland lies at nearly 60 degrees north latitude, making it one of the most challenging inhabited regions in prehistoric Europe. Winters are long, storms are frequent, and agricultural opportunities are limited compared to southern Britain. Yet, generation after generation returned to the same coastal position. Modern environmental studies suggest the area provided a rare combination of sheltered landing places, access to fishing grounds, freshwater sources, and relatively productive grazing land. However, many locations across Shetland possess similar advantages. The persistence of Jarlshof hints that ancient communities may have recognized strategic environmental qualities that archaeologists still do not fully understand. The engineering of the settlement itself presents another puzzle. The earliest inhabitants constructed houses partially sunk into the ground, a design that appears simple until examined through modern thermodynamic principles. By embedding structures within the earth and surrounding them with thick stone walls, builders created a passive temperature control system. Soil acts as a thermal buffer, reducing temperature fluctuations throughout the year. Modern energy-efficient architecture uses similar concepts under the name thermal mass design. Temperature simulations suggest that partially subterranean houses can reduce heat loss by as much as 30 to 50% compared with fully exposed structures in harsh northern climates. The people of Jarlshof achieved this thousands of years before the development of formal engineering theory. Researchers continue to debate whether this knowledge emerged through generations of experimentation or through traditions inherited from even earlier populations whose settlements have not survived. The layout of the Iron Age village raises additional questions. archaeologists uncovered an intricate network of interconnected structures, passages, storage chambers, and built-in stone furniture. Many rooms contain wall recesses, carefully positioned compartments, and symmetrical arrangements that appear too deliberate to be accidental. Some houses seem designed around highly organized domestic activities, suggesting a level of spatial planning far more sophisticated than the stereotypical image of prehistoric communities. Certain architectural patterns repeated across multiple generations despite changes in population and culture. The persistence of these design principles implies the existence of architectural traditions transmitted across centuries, yet no written records survive to explain how such knowledge was preserved. Perhaps the most visually impressive engineering achievement is the broch. During the Iron Age, the inhabitants constructed a massive circular stone tower now known as the Jarlshof broch. Although only part of the structure survives, comparisons with better preserved examples indicate it may once have risen more than 10 meters high. Brochs remain among the most enigmatic buildings in Northern Europe. Their walls often exceeded 4 meters in thickness and incorporated internal stairways, galleries, and chambers. Unlike Roman buildings, they were constructed without mortar. Instead, thousands of carefully selected stones were fitted together with remarkable precision. Modern structural analyses show that the inward curving profile of broch walls distributed weight efficiently and enhanced stability against strong winds. The mystery lies in construction logistics. Even a modest broch required the extraction, transport, and placement of thousands of tons of stone. No evidence exists for cranes, advanced lifting mechanisms, or large draft animals. Yet these towers were built across northern Scotland with extraordinary consistency. How small island communities organised such labour remains only partially understood. Another technological puzzle emerges from the site's water management systems. Shetland receives substantial rainfall throughout the year, and poorly designed settlements quickly become waterlogged. Excavations at Jarlshof revealed drainage channels and engineered pathways directing water away from living areas. Some of these features remained functional after centuries of burial. Effective drainage may seem unremarkable today, but in prehistoric environments it represented a crucial survival technology. Similar hydraulic planning is often celebrated in Roman cities or Bronze Age palaces such as Knossos. Finding comparable attention to water control within a remote northern settlement challenges assumptions about the technological capabilities of small-scale societies. Yet the greatest mystery of Jarlshof lies not in its architecture but in its metallurgy and trade networks. This is where the site becomes truly extraordinary. For much of prehistory, Shetland occupied what appears on a modern map to be the edge of Europe. From a technological perspective, however, Jarlshof may have been connected to a surprisingly vast world. Excavations uncovered ironworking debris, metal tools, evidence of smithing, and imported artifacts originating far beyond the islands themselves. During the Viking Age, the settlement became integrated into maritime networks stretching across the North Atlantic. Objects found at Jarlshof reveal connections with Norway, the British mainland, Ireland, and possibly regions even farther south. The technological implications are profound. Iron production is not a simple craft. Creating usable iron requires locating ore, constructing furnaces capable of reaching temperatures above 1,150 degrees Celsius, controlling airflow, managing charcoal supplies, and mastering complex forging techniques. Every stage demands accumulated technical knowledge. Even minor mistakes in furnace design can ruin an entire batch of metal. Archaeological evidence suggests that skilled metal workers operated within the settlement, yet Shetland itself lacked many of the resources associated with major metallurgical centres. This raises a fundamental question. Where did the expertise originate? One possibility is that specialist craftsmen travelled through Viking trade routes, carrying knowledge from Scandinavia and other regions. Another theory proposes that technological skills were transmitted through family lineages over generations. Neither explanation fully accounts for the sophistication observed. Viking maritime routes connected communities separated by hundreds or even thousands of kilometres. Some voyages between Norway and Shetland covered more than 300 kilometres of open ocean. Navigation occurred without compasses, accurate maps, or modern instruments. Nevertheless, these networks transported not only goods but also ideas, technologies, and manufacturing techniques. The scale of this exchange becomes even more impressive when compared with other contemporary societies. During the early medieval period, many inland communities rarely interacted with populations more than a few dozen kilometres away. By contrast, Viking sailors routinely crossed vast stretches of ocean. Archaeological studies estimate that some North Atlantic trade routes connected settlements separated by distances exceeding 1,500 kilometres. Through these connections, innovations in shipbuilding, metallurgy, woodworking, and agriculture could spread rapidly. Jarlshof appears to have been part of this knowledge network. The settlement may have functioned not merely as a remote village but as a node in an international system of technological exchange. Northeastern Azerbaijan holds the ruins of Chirag Gala, a fortress standing more than 1,200 meters above sea level, surrounded by cliffs, violent winds, and steep volcanic stone ridges. From a distance, it looks impossible. A massive military complex built on terrain where even modern construction equipment would struggle to operate. Yet for nearly 15 centuries, its walls resisted earthquakes, erosion, invasions, and extreme weather. Even stranger historians believe this isolated fortress may once have been part of an ancient long-distance communication network capable of transmitting warning signals across the Caucasus Mountains long before modern telecommunications existed. Today, many archaeologists consider Chirag Gala one of the least understood military engineering sites of the early medieval world. Although local communities had known about the ruins for centuries, systematic archaeological surveys only intensified during the 20th century under Soviet-era Caucasus expeditions. Researchers quickly realized the fortress was far larger and more sophisticated than previously assumed. Built during the period of the Sassanid Empire, likely between the 5th and 6th centuries AD, Chirag Gala occupied a strategic position overlooking routes connecting the Caspian coast to the northern Caucasus frontier. Excavations uncovered defensive walls, towers, reservoirs, stone foundations, and evidence of prolonged military occupation. But the deeper archaeologists investigated, the more puzzling the site became. The fortress was not simply placed on the mountain, it was engineered into the mountain itself. The most controversial theory surrounding Chirag Gala involves its possible use as part of an ancient optical communication network. The name Chirag Gala is often translated as Fortress of Light or Lamp Fortress. Historians believe this may not be symbolic. Instead, it could describe the actual function of the structure. From the highest towers, observers can see enormous stretches of surrounding terrain, including distant mountain corridors and lowland approaches near the Caspian basin. Modern topographic analysis suggests visibility lines from Chirag Gala overlap with several other ancient fortified positions scattered across the Caucasus. This has led some researchers to propose that the Sassanids created a chain of mountaintop signal stations capable of relaying warnings across hundreds of kilometers. The concept itself sounds surprisingly advanced for the 6th century. Yet historically, long-distance visual signaling systems did exist in ancient civilizations. The Byzantine Empire later used beacon chains across Anatolia. Ancient China developed smoke signal towers along frontier defenses. Even the Greeks experimented with coded torch systems described by Polybius more than 2,000 years ago. But Chiragala presents unusual technical challenges. The Caucasus Mountains are notorious for heavy fog, sudden storms, and unstable visibility conditions. Maintaining reliable communication under such conditions would require extremely precise positioning of observation towers. Researchers using satellite mapping discovered that several fortress locations appear intentionally placed within direct visual range of one another despite the difficult terrain. This suggests the builders understood line-of-sight geometry at a sophisticated level. Some historians speculate that signal fires may have been amplified using polished metal reflectors or shielded beacon chambers designed to increase visibility at long distances. Others believe coded smoke pulses or sequential torch patterns may have been used to transmit specific military warnings. No surviving written manual explaining the system has ever been found. What makes the mystery even more fascinating is the speed such a network could theoretically achieve. A mounted messenger traveling through mountain terrain might require days to deliver military information. But a relay system using sequential fire signals could potentially transmit warnings across frontier regions within hours or even minutes under ideal conditions. For an empire constantly threatened by northern invasions, such speed would have been revolutionary. If the theory is correct, Chiragala may represent one of the most advanced early warning systems of the ancient Caucasus world. The fortress itself raises enormous engineering questions. Transporting construction materials to such altitude would have been extraordinarily difficult. Many surviving stone blocks weigh several hundred kilograms. Some wall sections sit directly beside vertical cliff faces, where there is barely enough space for modern hikers to stand safely, yet the masonry remains remarkably stable. Unlike conventional fortifications built on flat ground, the walls of Chiragala follow the mountain's natural geometry. Instead of forcing straight defensive lines, the builders adapted every section to the rock beneath it. Angles shift constantly, foundations curve around cliffs. Defensive corridors merge into natural stone barriers. This adaptive construction technique resembles certain high-altitude fortresses found in Iran and parts of the Byzantine frontier, but Chiragala's terrain is arguably even more extreme. Engineers studying earthquake-resistant ancient architecture have noted another unusual feature. Many sections lean slightly inward rather than standing perfectly vertical. Modern structural simulations show this inward angle may help distribute seismic stress more effectively during earthquakes. Considering the Caucasus region experiences frequent tectonic activity, this may not have been accidental. The builders appear to have understood principles of load distribution and geological stability centuries before formal structural engineering existed. One of the greatest mysteries surrounding Chiragala is survival. How could a fortress on such a barren mountain sustain soldiers for long periods? Archaeologists discovered reservoirs and water storage systems carved directly into the rock, but rainfall alone may not have been sufficient for a permanent garrison. This has triggered theories that the fortress used advanced water harvesting techniques or hidden spring collection systems inside the mountain itself. Some cistern interiors contain traces of unusual waterproof coatings. Similar ancient hydraulic coatings have been identified in Sassanid and Roman engineering projects, often involving combinations of lime, ash, mineral dust, and organic additives. What makes Chiragala remarkable is the durability of these systems under harsh mountain conditions. Even after more than 1,000 years of freeze-thaw cycles, parts of the water infrastructure remain identifiable. Some researchers compare the mystery to the durability of Roman concrete, which continues to puzzle materials scientists today because of its unexpected resistance to chemical erosion. If Chiragala possessed an efficient mountain water management system, it would explain how the fortress could operate during prolonged sieges despite its isolated location. The location of Chiragala may also have served psychological purposes. Any invading force approaching from below would see massive stone walls emerging directly from the mountain ridges. From certain angles, the fortress appears almost fused with the landscape itself. Military historians believe this visual dominance may have been intentional. Ancient defensive architecture often relied not only on physical barriers but also intimidation. At Chiragala, attackers face steep ascents under constant exposure from elevated defenders. Even small defending forces could potentially control narrow access routes with devastating efficiency. Some surviving tower positions suggest overlapping observation zones capable of monitoring multiple valleys simultaneously. This resembles later medieval kill zone strategies, yet Chiragala predates many of those systems by centuries. Its builders may have created one of the earliest examples of terrain-integrated mountain warfare architecture in the Caucasus region. Modern drone surveys indicate the visible ruins may represent only a fraction of the original system. Satellite imaging has revealed traces of collapsed walls, terraces, and possible lower defensive positions extending down the mountainside. Erosion and landslides may have buried major sections of the complex beneath rock and sediment. Some archaeologists suspect Chiragala was not an isolated fortress at all, but part of a vast defensive chain protecting the northern frontier of the Sassanid Empire against nomadic incursions from the Eurasian steppes. This theory aligns with other regional fortifications, including massive defensive systems near Derbent, sometimes called the Caspian Gates. Together, these structures may have formed one of the largest coordinated frontier defense systems of the ancient world. Yet large portions remain unexplored because of dangerous terrain and limited excavation access. What do you think Chiragala truly was? Just a mountain fortress, or part of a forgotten ancient communication network far ahead of its time? Share your thoughts in the comments below. Tinkinswood Chambered Tomb is a monument that seems impossible for the people who built it. Standing in the countryside of the Vale of Glamorgan in southern Wales, this Neolithic tomb has survived for more than 5,000 years. Archaeologists know when it was constructed. They know what it was used for. They can measure every stone, calculate every angle, and estimate every weight. Yet one fundamental question remains unanswered. How did a farming society with no metal tools, no wheels, and no written language create a structure capable of moving and supporting one of the largest prehistoric capstones in Britain? The deeper researchers investigate Tinkinswood, the more it challenges traditional assumptions about the technological abilities of Europe's earliest builders. The modern story of Tinkinswood began in 1914 when archaeologist John Ward conducted one of the first major excavations of the monument. Located approximately 10 kilometres west of Cardiff, the site sits on a limestone ridge overlooking fertile lowlands that would have supported Neolithic farming communities around 3600 BCE. Excavations revealed a long burial chamber hidden beneath what was once an earthen mound nearly 40 meters long. Human remains, pottery fragments, and stone tools were recovered from the site. Analysis suggested that the tomb had been used repeatedly over many centuries. Yet what immediately captured attention was not the burial evidence. It was the enormous stone roof covering the chamber. The capstone of Tinkinswood measures approximately 7.3 meters in length and weighs an estimated 40 tons. Some calculations place the weight even higher depending on the density of the local limestone. To understand the scale of this achievement, consider that the average African elephant weighs around 6 tons. The capstone therefore weighs roughly the equivalent of 6 or 7 adult elephants balanced above a narrow stone chamber. It remains one of the largest surviving capstones in Britain and among the heaviest ever used in a Neolithic monument in Western Europe. The first mystery concerns transportation. Geological studies indicate that the stones likely originated from local outcrops, but local does not necessarily mean nearby. Even moving a 40-ton block a few hundred meters across uneven terrain presents an enormous engineering challenge. Modern engineers can estimate the forces involved. On wooden rollers, a stone of this size could require hundreds of people pulling simultaneously. On a sled dragged across prepared ground, friction alone would create tremendous resistance. Experimental archaeology has demonstrated that prehistoric communities could move large stones using ropes, timber rollers, earthened ramps, and coordinated labour. However, no experiment has perfectly recreated the transport of a capstone matching the dimensions and weight of Tinkinswood's roof stone. The exact method remains unknown. The challenge becomes even greater when considering elevation. Transporting a 40-ton stone is one problem. Raising it into position is another entirely. The capstone sits atop upright stones forming the burial chamber. To achieve this, builders may have gradually increased the height of an earthen ramp, dragging the stone upward before removing the supporting soil. Similar theories have been proposed for megalithic monuments across Europe. Yet every reconstruction faces difficulties. A ramp large enough to lift a 40-ton stone would require moving vast quantities of earth. Such a project demands planning, labour organisation and engineering foresight on a scale rarely associated with small Neolithic communities. Perhaps even more remarkable than the construction itself is the monument's structural stability. For more than 5 millennia, the capstone has remained largely intact despite exposure to weather, temperature fluctuations, biological growth and ground movement. Engineers studying megalithic structures often note that longevity depends on effective load distribution. At Tinkinswood, the weight of the roof stone is transferred through carefully positioned supporting slabs. The builders may not have understood structural mechanics in mathematical terms, but they clearly possessed practical knowledge acquired through observation and experience. The result is a monument that has outlasted kingdoms, empires, and entire civilizations. Comparison with other Neolithic monuments highlights the unusual nature of Tinkinswood. At Stonehenge, many of the largest stones weigh between 20 and 30 tons. Several of Tinkinswood's components approach or exceed this range, despite being constructed centuries earlier. Across Atlantic Europe, chambered tombs are common, yet few possess a single capstone of comparable size. Newgrange in Ireland, Maeshoa in Scotland, and Gavrinis in France demonstrate extraordinary prehistoric engineering. But Tinkinswood remains distinctive because so much of the structure's weight is concentrated in one enormous stone. Another mystery concerns surveying and alignment. The tomb was not assembled randomly. The chamber follows a deliberate orientation, and the surrounding mound was constructed according to a coherent architectural plan. Achieving such precision without modern measuring devices required sophisticated observational techniques. Archaeologists have proposed that Neolithic builders used ropes, wooden stakes, sighting poles, and geometric methods derived from repeated practice. While simple in theory, these techniques can produce surprisingly accurate results when applied by skilled builders. The problem is that no direct evidence survives showing exactly how Tinkinswood's designers measured distances, maintained symmetry, or ensured stability during construction. The burial evidence introduces another layer of mystery. Excavations revealed remains representing at least 50 individuals, but estimates suggest that as many as 800 or even 1,000 people may have been interred at the site over centuries of use. This raises important questions about social organization. A monument of this scale requires cooperation among large groups of people. The construction alone may have involved hundreds of workers. Maintaining the site for generations implies the existence of traditions, leadership structures, and systems of knowledge transmission capable of preserving architectural practices across many lifetimes. Researchers have also investigated the acoustic properties of chambered tombs. Studies conducted at several Neolithic monuments have shown that enclosed stone chambers can create unusual resonance effects. Low-frequency sounds, chanting and drumming may be amplified within confined spaces. Although detailed acoustic testing at Tinkinswood remains limited compared with sites such as Newgrange, the possibility raises intriguing questions. Did the builders intentionally exploit sound during ceremonies? Were architectural decisions influenced not only by structural requirements, but also by ritual experiences created within the chamber? Definitive answers remain elusive. The technological puzzle deepens when considering the tools available to the builders. Around 3600 BCE, metalworking had not yet become widespread in Britain. Construction depended primarily on stone tools, wooden implements, antler picks, ropes made from plant fibers, and human labor. Yet the finished monument demonstrates levels of planning and execution that appear remarkably advanced. This does not mean the builders possessed lost technologies or unknown machines. Rather, it suggests that modern observers may underestimate the capabilities of prehistoric engineering traditions developed over countless generations.
In eastern Anatolia, beside the immense blue waters of Lake Van, a wall of stone rises abruptly from the landscape. At first glance, it looks less like a fortress and more like a natural mountain split open by geological violence. But carved into the side of that cliff are stairways, chambers, inscriptions, and defensive walls belonging to Tushpa Fortress, the ancient capital of the Urartian kingdom, built nearly 3,000 years ago. What makes Tushpa so unsettling is not simply its age, it is the engineering. Even today, archaeologists and structural historians still debate how a civilization of the early Iron Age managed to carve, transport, and construct on terrain that modern engineers would consider extremely hostile. The first large-scale modern investigations of Tushpa began in the 19th century when European explorers travelling through the Ottoman Empire documented strange inscriptions cut high into the cliffs above Van. Early travellers believed the ruins belonged to Assyrians because the writing resembled Mesopotamian cuneiform. But in the 1820s and later through expeditions in the 1870s, researchers discovered that the inscriptions referenced kings of a previously misunderstood civilization, Urartu. Each excavation season revealed something new. One expedition uncovered rock-cut royal tombs hidden deep within the mountain. Another revealed massive cisterns and hydraulic channels. Later surveys found defensive terraces and stone foundations stretching across the cliffside, proving that Tushpa had once been a heavily fortified royal complex rather than a simple military outpost. The deeper archaeologists dug into Tushpa, the stranger the fortress became. The first mystery was the mountain itself. The citadel stands on a limestone ridge more than 100 meters high and nearly 2 kilometers long. The slopes are steep enough that in many areas even modern climbing equipment is required for safe access. Yet the Urartians somehow transformed this natural rock formation into a functioning royal capital. They carved staircases directly into vertical stone faces, some with remarkably even step geometry, despite severe erosion over thousands of years. In certain sections, the cuts are so straight that researchers compared them to later Roman quarrying techniques, even though the Romans would not dominate Anatolia until centuries later. This is where the technological debate begins. Iron Age tools in the 9th century BCE were still relatively primitive compared to later classical civilizations. Experimental archaeologists attempting to reproduce Urartian stone-cutting methods found that shaping hard limestone with early iron chisels required enormous labor and produced inconsistent surfaces. But many chambers in Tushpa display unusually smooth internal walls and sharply defined angles. Some cuts run several meters with almost no visible deviation. That level of precision becomes even more difficult to explain, considering many of these chambers were carved in confined spaces with minimal natural light.
Among the most mysterious discoveries were the royal tomb chambers hidden inside the rock. These rooms were not built with stacked stone blocks like Egyptian pyramids or Mycenaean tombs. Instead, they were excavated directly into the mountain itself. The entrances are positioned high above the ground, accessible only through narrow carved pathways. Archaeologists still debate how workers transported tools, food, water, and illumination equipment into those spaces during construction. Some tombs contain ceilings and corners, approaching near-perfect geometric symmetry. Even slight angular errors during excavation would have ruined the chambers permanently because the rooms were carved from solid bedrock rather than assembled piece by piece. The engineering challenge becomes even more astonishing when compared to other ancient cliff structures. Persian royal tombs at Naqsh-e-Rostam also used rock-cut architecture, but most date centuries later than Tushpa. Egyptian burial chambers often relied on broader excavation corridors and flatter terrain. Tushpa combined elevation, confined carving spaces, and steep mountain geometry all at once, making the fortress one of the most technically difficult construction sites of the ancient Near East. Then came the water mystery. Tushpa overlooks Lake Van, but the fortress itself sits far above the shoreline on dry, exposed stone. A large settlement at that elevation would require enormous quantities of water for drinking, storage, livestock, and defense. Yet excavations uncovered reservoirs, cisterns, and evidence of sophisticated hydraulic systems integrated into the fortress. Researchers believe the Urartians connected Tushpa to broader canal networks built throughout the kingdom. The most famous example is the Menua Canal, an engineering project more than 50 kilometers long that still carries water in some areas nearly 28 centuries later. What astonishes engineers is the precision of those gradients. Modern hydraulic analysis showed that several Eurasian canals maintained carefully controlled slopes that allowed water to flow steadily without destroying the channel walls through erosion. In some sections, the incline variation is measured in fractions of a degree across long distances. Comparable hydraulic accuracy would later become famous in Roman aqueduct systems. Yet the Urartians achieved similar functionality centuries earlier in mountainous terrain, using surveying methods that remain poorly understood. Some archaeologists believe the Urartians used primitive astronomical alignment and long-distance sighting techniques to calculate elevation changes. Others argue they developed practical engineering traditions through generations of trial and error. But no theory fully explains how such precise hydraulic control was maintained over rugged volcanic terrain without advanced instruments. But Tushpa's greatest strength may have been its military engineering. Most ancient fortresses relied on walls. Tushpa weaponized geography itself. Instead of leveling the mountain, the Urartians modified the terrain to create defensive choke points, steep approach corridors, and elevated firing positions. Certain access routes force attackers into narrow, exposed pathways, overlooked from above. Military historians have compared aspects of Tushpa's defensive logic to medieval hill fortresses built over 1,000 years later. The difference is that Urartu developed these concepts during a period when organized siege warfare was still evolving across much of the Near East. The layout suggests a sophisticated understanding of visibility, movement restriction, and terrain manipulation. Even today, modern soldiers studying ancient warfare note that assaulting Tushpa directly would have been devastatingly difficult without prolonged siege tactics. In many places, gravity itself became part of the fortress defense system. Excavators also discovered enormous stone blocks positioned in places that remain difficult to explain. Some wall sections contain multi-ton stones transported onto elevated terraces where maneuvering space is extremely limited. The region surrounding Lake Van is rugged, uneven, and prone to severe winter conditions. Traditional theories suggest the Urartians used wooden rollers, sledges, and earthen ramps.
However, no experimental reconstruction has fully demonstrated how those techniques could consistently move such heavy material onto the steepest areas of the fortress without catastrophic collapse or loss of control. Comparisons with Inca stone transport in Peru often emerge in academic discussions because both civilizations operated in mountainous environments. But while the Inca relied heavily on polygonal masonry and broader mountain roads, Tuxpa's terrain is narrower and more vertically restrictive. That difference makes the logistics of Urartian construction even harder to reconstruct experimentally. Adding to the mystery are the inscriptions carved directly into exposed cliff faces. One of the most famous texts belongs to King Sarduri. The inscription sits high above the ground in a location so difficult to access that early travelers required ropes just to approach it. Yet the cuneiform characters are strikingly uniform in depth and spacing. Creating such inscriptions would have required stable platforms or scaffolding systems, but almost no physical evidence of those support structures survived. Historians suspect the Urartians developed advanced wooden scaffolding techniques adapted specifically for cliff construction, though the exact methods remain unknown. The precision of the inscriptions is especially important because uneven carving on exposed stone normally leads to accelerated erosion. Yet many Urartian characters remain legible after nearly 3,000 years of wind exposure, temperature shifts, and seismic activity around Lake Van.
Late Bronze Age collapse is one of the greatest mysteries in human history. Stretching across the eastern Mediterranean, from Greece and Anatolia to Egypt, the Levant and Mesopotamia, it was not the destruction of a single kingdom, but the sudden collapse of an entire interconnected world. Around 1200 BC, some of the most advanced civilizations on Earth began to disappear within just a few generations. Cities burned, palaces were abandoned, trade routes vanished, writing systems fell silent, and technologies that had taken centuries to develop seemed to dissolve almost overnight. What makes this event so extraordinary is that it happened during an age that many historians now compare to an ancient version of globalization. The question is not simply why these civilizations collapsed. The real mystery is how a world so technologically sophisticated could unravel so completely. The discovery of this catastrophe did not come from a single archaeological excavation. During the 19th and 20th centuries, archaeologists working across Greece, Turkey, Syria, Israel, and Egypt repeatedly uncovered the same pattern. Prosperous cities showed evidence of destruction within a relatively narrow time frame. At first, these events appeared unrelated, but as more sites were excavated and radiocarbon dating improved, a startling picture emerged. Entire civilizations had experienced a dramatic breakdown between approximately 1200 and 1150 BC. It was one of the largest systemic collapses ever documented in the ancient world. Before examining the mystery itself, it is important to understand how advanced the Late Bronze Age really was. Popular imagination often portrays this era as primitive, but archaeological evidence tells a very different story. By the 13th century BC, the Eastern Mediterranean was connected through vast commercial networks spanning thousands of kilometers. Diplomatic letters traveled between kings, merchant ships crossed open seas carrying cargoes worth fortunes. Engineers constructed massive fortifications, palaces, harbors, and irrigation systems. Governments maintained administrative records using complex writing systems. In many respects, this was one of the most technologically interconnected societies humanity had ever created. One of the most remarkable discoveries illustrating this sophistication is the Uluburun shipwreck, found off the coast of modern Turkey. Dated to approximately 1300 BC, the vessel carried over 10 tons of copper ingots, roughly 1 ton of tin, glass ingots, ivory, ebony, jewelry, and luxury goods originating from multiple regions. Scientific analysis suggests that materials aboard the ship came from Cyprus, Egypt, the Levant, Mesopotamia, and possibly even farther away. This single vessel demonstrates that Bronze Age trade networks stretched across an enormous geographic area. Yet hidden within its cargo lies perhaps the greatest technological mystery of the entire collapse. Bronze was the foundation of civilization. Weapons, tools, armor, agricultural equipment, and countless other products depended upon it. Producing bronze required a mixture of copper and tin. Copper was relatively abundant. Tin was not. In fact, tin was one of the rarest strategic resources in the ancient world. Most Bronze Age civilizations possessed little or no local supply. Yet year after year, century after century, vast quantities of tin somehow arrived exactly where they were needed. The mystery deepens when researchers attempt to identify the source. Unlike copper mines, many ancient tin sources remain uncertain. Some evidence points towards Central Asia. Other studies suggest deposits in Afghanistan. Isotopic analysis has connected certain artifacts to regions thousands of kilometers from where they were ultimately discovered. Even more surprising, some researchers have proposed that a portion of Bronze Age tin may have originated in Cornwall in southwestern Britain, over 4,000 kilometers away from major Mediterranean centers. If this hypothesis is correct, then ancient traders maintained supply chains stretching farther than many historians once believed possible. This raises a question that remains unanswered even today. Who coordinated these networks? There was no global empire. There were no modern maps, no compasses, no banks, and no centralized international institutions. Yet somehow, merchants, sailors, miners, and rulers sustained one of the most complex resource distribution systems of the ancient world. The movement of tin resembles a logistical miracle. Thousands of tons appear to have traveled across mountains, deserts, rivers, and seas with remarkable consistency. Then, almost suddenly, the system failed. Archaeological evidence suggests that after the collapse, tin became dramatically less common throughout many regions. Bronze production declined. Long-distance trade shrank. Some scholars argue that the interruption of tin supply may have triggered cascading failures throughout the entire Mediterranean economy. Imagine a modern world suddenly losing access to semiconductors, oil, or electricity. Entire industries would grind to a halt. In many ways, tin may have been the Bronze Age equivalent of a critical technological resource upon which everything depended. The disappearance of technological knowledge is equally puzzling. Following the collapse, many sophisticated administrative systems vanished. In Mycenaean Greece, the Linear B writing system disappeared entirely. Monumental palace construction ceased. Trade networks fragmented. Population levels declined in numerous regions. Some communities returned to smaller, less complex forms of organization. Historians often refer to the centuries following the collapse as a dark age, not because people vanished, but because much knowledge appears to have been lost. What makes this especially strange is that technological knowledge does not usually disappear so completely. The Egyptians knew how to build monumental architecture. The Hittites mastered advanced metallurgy. The Mycenaeans operated highly organized bureaucracies. Yet after the collapse, many of these achievements became rare or disappeared altogether. Archaeologists continue debating whether this represents actual technological regression or merely the loss of centralized institutions capable of preserving and transmitting expertise. Adding another layer of mystery are the enigmatic sea peoples. Ancient Egyptian inscriptions describe large groups arriving by sea and attacking multiple regions across the Mediterranean. Reliefs from the reign of Pharaoh Ramesses III depict fierce battles against these invaders around 1177 BC. However, Despite more than a century of research, scholars still cannot definitively identify who the Sea Peoples were. They may have been migrants fleeing famine, they may have been displaced populations driven by environmental pressures, they may have been mercenaries, raiders, or entire communities seeking new lands. The evidence remains frustratingly incomplete. The Sea Peoples are particularly intriguing because they appear precisely when the wider system was already under stress. Their attacks may have accelerated existing weaknesses rather than caused the collapse outright. In this sense, they resemble a final shock, striking a structure that was already unstable. Yet because their origins remain uncertain, they continue to occupy one of the most mysterious positions in ancient history. Climate evidence has introduced another possible explanation. Sediment cores, pollen records, cave formations, and tree ring studies indicate that parts of the eastern Mediterranean experienced severe droughts around the time of the collapse. Some regions may have endured decades of reduced rainfall. Agricultural production likely suffered. Food shortages could have triggered migration, unrest, and conflict. However, climate data does not provide a complete answer. Some areas show stronger evidence of drought than others. The timing is not perfectly consistent everywhere. Environmental stress appears important, but it does not fully explain why entire political and technological systems failed simultaneously. Modern researchers increasingly view the Late Bronze Age collapse as a failure of complexity itself. The interconnected world of 1200 BC may have become so dependent upon long-distance trade, specialized labor, resource imports, and political stability that even small disruptions could trigger catastrophic consequences. Computer models of complex systems demonstrate that highly interconnected networks often become vulnerable to cascading failures. When one critical component collapses, others follow. The Bronze Age world may represent the earliest known example of such a phenomenon on a continental scale. One of the most striking aspects of the Late Bronze Age collapse is that major civilizations seemed unprepared. Despite their power and advanced systems, the Egyptians, Hittites, and Mycenaeans failed to recognize how fragile their interconnected world had become. Within a few decades, cities were abandoned, trade collapsed, and valuable knowledge was lost. What do you think was the single most important factor behind the Late Bronze Age collapse? Climate change, war, economic breakdown, the loss of critical resources like tin or something else entirely? Share your theory in the comments below. Golubak Fortress is one of the most strategically positioned fortresses ever built in medieval Europe. Standing on the right bank of the Danube River in eastern Serbia, at the entrance to the Iron Gates Gorge, the fortress occupies a location where geography, engineering, and military architecture converge in ways that still challenge modern understanding. For centuries, armies fought to control it, empires rebuilt it, and engineers modified it. Yet some of the knowledge that made its construction possible remains surprisingly difficult to explain. The fortress dominates a narrow section of the Danube where the river begins its transition into the Iron Gates, one of Europe's largest river gorges. Today, visitors see 10 towers rising above steep limestone cliffs, but the most fascinating story is not what survives. It is how medieval builders managed to construct, reinforce, and maintain such a complex defensive system on terrain that appears almost impossible for large-scale construction. The existence of Golubak was documented in medieval records beginning in the 14th century, although archaeological evidence suggests earlier fortifications may have occupied the site long before the fortress reached its final form. Excavations, restoration projects, geological surveys, and modern laser scanning have revealed numerous construction phases associated with Serbian, Hungarian, and Ottoman control. Yet every new discovery seems to generate additional questions about the engineering capabilities of its builders. The first mystery concerns the fortress's location itself. Many medieval castles were built on hills, but Golubac occupies a far more difficult environment. Portions of the fortress rise directly from limestone cliffs overlooking the Danube, and some towers stand on slopes approaching angles that would challenge modern construction equipment. Engineers today rely on cranes, reinforced concrete foundations, geotechnical drilling, and computer simulations when building on similar terrain, but medieval builders possessed none of these technologies. Researchers estimate that thousands of tons of stone were transported and positioned during construction and expansion phases, yet the exact methods remain unknown. Historical records provide no detailed construction manuals, and no contemporary blueprints survive. Nevertheless, the fortress demonstrates remarkable adaptation to natural topography. Rather than forcing the landscape to conform to a standard design, builders integrated walls, towers, and defensive positions directly into the existing rock formations. This suggests a sophisticated understanding of structural stability. The builders appear to have recognized which sections of bedrock could support heavy masonry and which areas required reinforcement. Such knowledge normally develops through generations of accumulated practical experience, but the challenge is that very little documentation survives explaining how that knowledge was transmitted. The second mystery involves the unusual tower system. Golubac contains 10 primary towers, but unlike many medieval fortifications, they are not uniform in shape. Some towers are square, others are polygonal, and several display evidence of major modifications. Historians traditionally explained these differences as the result of construction occurring over multiple centuries. While this is undoubtedly true, modern architectural analysis suggests something more complex. The positioning of certain towers appears optimized for overlapping fields of fire and observation. Their arrangement takes advantage of natural blind spots created by the terrain, and in several cases, the shape of a tower may have been influenced by local geological conditions rather than purely military considerations. This raises an important question. How sophisticated were medieval surveyors working at Golubac? Modern topographic studies indicate that even small errors in tower placement could have created defensive weaknesses. Yet the fortress maintained effective coverage across critical approaches from both land and river. Achieving such precision without modern surveying instruments remains an impressive accomplishment. The third mystery centers on the Danube itself. Golubac was not merely a fortress, it was also a mechanism for controlling one of Europe's most important transportation corridors. Historical sources describe the existence of a massive chain stretched across the Danube near the fortress. Similar systems existed elsewhere in medieval Europe, but Golubac's location made such a barrier particularly effective. The river narrows significantly before entering the Iron Gate's gorge, creating a natural choke point for commercial and military traffic. The engineering challenges associated with this system are rarely discussed. The Danube is Europe's second longest river, extending approximately 2,850 kilometers. Its flow can exert enormous force on any obstacle placed across its channel. A chain capable of stopping ships would require advanced ironworking techniques, secure anchoring systems, and mechanisms for raising and lowering enormous weights. No complete remains of this system survive. Consequently, historians still debate exactly how it functioned. Was the chain permanently installed or deployed only during emergencies? How were its anchor points reinforced? What mechanical systems assisted operators? These questions remain largely unanswered. The fourth mystery, and perhaps the most overlooked, is the technology behind the fortress's mortar. When visitors look at Golubac, they naturally focus on the towers and walls. Yet the true secret of the fortress may lie in the material holding those stones together. Mortar is often treated as a secondary component in ancient and medieval construction. In reality, it frequently determines whether a structure survives for centuries or collapses within decades. Golubac has endured earthquakes, warfare, seasonal flooding, extreme temperature fluctuations, moisture infiltration, biological growth, and continuous exposure to wind coming through the Danube corridor. Despite these conditions, significant portions of the masonry remain intact. Materials scientists studying historic structures have repeatedly discovered that ancient builders sometimes produced mortars with properties that are difficult to replicate precisely today. The Roman Empire provides perhaps the most famous example. Roman marine concrete has survived for nearly 2,000 years in aggressive coastal environments, while many modern concretes deteriorate far more quickly. Analysis revealed that volcanic ash, lime, and complex chemical reactions contributed to the material's extraordinary durability. Golubac presents a similar puzzle on a smaller scale. Laboratory studies of medieval mortars across the Balkans have shown that builders often combined lime with carefully selected aggregates and occasionally organic additives. Animal products, plant fibers, charcoal particles, brick dust, and other ingredients have been identified in historical mortars from various regions. The exact composition used at Golubac likely varied across different construction phases, but researchers continue investigating why some sections have survived exceptionally well despite centuries of environmental stress. One possibility is that local builders possess practical knowledge of limestone chemistry that was never formally documented. Another possibility is that generations of craftsmen refined mortar recipes through trial and error, gradually developing mixtures optimized for local climate conditions. The problem is that this knowledge was transmitted through apprenticeship rather than written technical manuals. When political systems changed, wars disrupted communities, or skilled craftsmen disappeared, much of that expertise vanished as well. The result is a paradox. Modern scientists can analyze surviving mortar at microscopic and chemical levels. They can identify minerals, measure porosity, examine crystal structures, and reconstruct manufacturing processes. Yet they still cannot fully recreate the cultural knowledge system that produced the material in the first place. The fifth mystery involves adaptation to gunpowder warfare. Golubac occupied a strategic frontier during the period when artillery was transforming military architecture across Europe and the Ottoman world. Many medieval castles became obsolete after the widespread introduction of cannons. High vertical walls that resisted arrows and siege engines proved vulnerable to concentrated artillery fire, and fortifications throughout Europe underwent major redesigns. Golubac demonstrates evidence of this transition. Certain towers were reinforced, wall thicknesses increased in some areas, and defensive layouts evolved to accommodate firearms and artillery. What fascinates historians is the speed with which these adaptations occurred. The fortress appears to have undergone continuous technical evolution as military technology changed, suggesting access to skilled engineers capable of understanding emerging threats and modifying existing structures accordingly. The sixth mystery concerns water management. Every major fortress requires a reliable water supply, and during a siege, access to water often determined survival. Golubac stood beside the Danube, yet proximity to a river does not guarantee security. Defenders needed protected access to water even when enemy forces controlled surrounding territory. Archaeological evidence indicates the presence of cisterns and water storage systems, but researchers continue debating how the fortress maintained long-term water security. Were hidden passages used to reach the river? Did engineers create sophisticated rainwater collection systems? Or were there additional hydraulic features that have yet to be discovered? The answers remain uncertain. On the eastern coast of the Black Sea, only a few kilometers from modern Batumi, the massive stone walls of Gonio Fortress rise from one of the wettest regions in the Caucasus. Archaeologists believe the fortress was originally built during the Roman expansion into Colchis around the 1st century CE, though deeper excavation layers suggest the site may be significantly older. The first major excavations in the 19th century uncovered Roman pottery, bronze coins, military barracks, drainage channels, and unusually advanced defensive structures. Later, Soviet-era surveys revealed underground tunnels and hidden construction layers beneath the visible Roman walls. Every excavation season seemed to expose something unexpected: older foundations, unexplained engineering solutions, or materials surviving far beyond their expected lifespan. Today, Gonio Fortress remains one of the least understood Roman frontier fortresses ever discovered around the Black Sea. One of the first mysteries surrounding Gonio is its survival itself. The fortress was constructed close to marshy coastal terrain, with heavy rainfall exceeding 2,000 millimeters annually in some years. Ancient fortifications built in such wet environments usually suffer severe foundation collapse after centuries. Yet large portions of Gonio's walls remain standing after nearly 2,000 years. Some wall sections are almost 5 meters thick and consist of massive basalt and limestone blocks fitted together with remarkable precision. Modern structural engineers studying the site found that the foundations distribute pressure unusually evenly, despite the unstable soil underneath. Certain lower layers appear to contain compacted gravel drainage beds, similar to techniques used in advanced Roman hydraulic construction. What makes this puzzling is location. Gonio stood at the far eastern edge of Roman influence, thousands of kilometers from Rome itself. Comparable engineering sophistication is usually associated with major Roman centers like Colosseum or the aqueduct systems of Segovia Aqueduct, not remote military outposts near the Caucasus Mountains. Some researchers argue that Roman engineers may have reused older local engineering knowledge already present in Colchis long before Roman occupation. During 20th century excavations, archaeologists uncovered one of the most surprising discoveries beneath the fortress: a sophisticated underground drainage network. The channels were constructed with baked clay pipes and carefully angled stone conduits, designed to remove rainwater rapidly from the interior. Measurements showed that some drainage slopes deviated by only a few millimeters over long distances. Even modern gravity-based drainage systems rely on similar precision. The mystery becomes deeper when climate data is considered. The eastern Black Sea coast experiences intense seasonal storms and extremely high humidity. Without efficient water management, a fortress of this scale would slowly collapse from erosion and internal flooding. Yet parts of Gonio's drainage system still function today. Researchers compared the hydraulic planning at Gonio with Roman systems discovered at Pompeii and Ephesus. The similarities were striking, especially in the use of layered sediment traps and runoff control. But unlike Pompeii or Ephesus, Gonio was never considered a major engineering center of the Roman world. That contradiction remains unexplained. Excavations in different sectors of the fortress repeatedly produced evidence that complicated the accepted history of the site. Early digs uncovered Roman military artifacts, including spearheads, armor fragments, and coins from the reign of Emperor Hadrian. Later excavations revealed Byzantine modifications, including reinforced towers and redesigned gate systems. Ottoman-era ceramics and firing positions were found in upper layers. But beneath all of those layers, archaeologists discovered something far more controversial: deeper stone foundations predating Roman occupation. Carbon dating of organic material trapped within some lower construction layers suggested parts of the site could date centuries earlier than the Roman fortress itself. Some pottery fragments resembled artifacts linked to the ancient Colchian civilization, the same civilization associated with Greek legends surrounding Jason and the Golden Fleece. If these findings are correct, the Romans may not have built Gonio from scratch. Instead, they may have expanded an already ancient stronghold whose original builders remain unknown. Gonio Fortress follows an almost perfectly rectangular layout covering roughly 4.5 hectares. 18 defensive towers were positioned around the perimeter with highly consistent spacing. Military historians studying the fortress noticed something unusual about the tower arrangement. The placement creates overlapping visual and projectile coverage zones, minimizing blind spots around the walls. In practical terms, defenders could attack approaching enemies from multiple angles simultaneously. This principle resembles the interlocking fields of fire concept widely used in early modern European fortress design more than 1,000 years later. The geometry also suggests advanced surveying capability. Creating near-perfect alignment across such a large structure without modern optical equipment would have required extremely accurate measurement methods. Roman surveyors were certainly skilled, but some archaeologists argue that Gonio demonstrates a level of regional military planning rarely seen in frontier fortresses. Another major mystery involves the durability of the fortress materials themselves. Gonio lies close to the Black Sea, where salty air, heavy rain, biological growth, and humidity rapidly destroy exposed stone structures. Many medieval fortifications in similar climates deteriorated severely within only a few centuries. Yet portions of Gonio's original masonry remain remarkably intact after nearly 2 millennia. Material analysis performed on mortar residues found traces of volcanic ash compounds rich in silica and aluminum. Some researchers compared the mixture to Roman pozzolanic concrete, famous for its ability to resist water damage. Roman marine concrete has survived over 2,000 years in Mediterranean harbours because of chemical reactions between volcanic minerals and seawater. The problem is geography. High-quality volcanic pozzolana sources were concentrated mainly around Italy. Scientists still debate how similar material technology may have appeared in a distant Caucasus fortress. Some theories suggest local engineers independently developed similar mixtures using regional volcanic sediments from the Caucasus volcanic belt. Others believe Roman military engineers transported specialized knowledge across the empire more effectively than historians once believed. Modern ground-penetrating radar surveys detected hidden cavities beneath sections of the fortress that remain unexcavated. Some of these underground spaces appear connected through narrow corridors running below the walls. Their exact purpose remains unknown. Possibilities include emergency escape tunnels, military storage chambers, hidden water reservoirs, or secret communication routes. The difficulty is that many sections are partially flooded or structurally unstable. Even with modern imaging technology, archaeologists still cannot fully map the underground network. Several unexplored anomalies continue appearing in geophysical scans, suggesting that significant portions of Gonio may still lie buried beneath centuries of sediment. The fortress is also linked to one of Christianity's oldest traditions. Local belief claims that the tomb of Saint Matthias, one of the 12 apostles of Jesus, lies somewhere within Gonio. No confirmed archaeological evidence has verified the claim, yet the tradition persisted for centuries across Byzantine and Georgian sources. Excavations near the supposed burial area uncovered ancient graves and religious structures, but nothing conclusively tied to Saint Matthias himself. This overlap between military engineering and sacred legend adds another layer to the mystery of the site. What do you think was the greatest mystery hidden inside Gonio Fortress? The advanced engineering, the underground tunnels, or evidence of an older lost civilization beneath the Roman walls? Share your thoughts in the comments below. Sudak Fortress is a medieval giant standing on a volcanic hill above the Black Sea coast of Crimea. More than 6 centuries after its construction, its walls still dominate the landscape. Yet the greatest mystery is not the fortress itself. It is how medieval engineers, working without modern surveying instruments, cranes, or scientific materials laboratories, created a defensive system so durable that large portions remain standing today. The fortress was never truly lost. Historical records from Genoese merchants described Sudak as one of the most important trading and military centres of the northern Black Sea. Archaeological investigations beginning in the 19th century and continuing through the 20th and 21st centuries revealed the complex engineering hidden within its walls, towers, water systems, and construction materials. Sudak Fortress occupies a volcanic rock formation, rising approximately 157 meters above sea level. The position appears almost perfectly engineered by nature itself. Steep cliffs protect three sides of the hill, leaving only a limited approach for attackers. Military historians often compare strategic locations like Sudak to famous strongholds such as Masada or Crac de Chevalier. Yet Sudak possessed an additional advantage. It overlooked major maritime trade routes connecting the Byzantine Empire, the Caucasus, Central Asia, and the Mediterranean. What remains unclear is how medieval surveyors evaluated the site so effectively. Without aerial photography, satellite imagery, or topographic mapping, they identified a location that maximized visibility, controlled trade routes, and minimized defensive vulnerabilities. Modern geographic information system analysis demonstrates that observers from the fortress could monitor vast sections of the surrounding coastline and see approaches. Such strategic optimization suggests a level of geographic knowledge far beyond what many people associate with the medieval period. Most people imagine a fortress as a single wall surrounding a settlement. Sudak was something entirely different. The fortress was organized into multiple defensive zones. Attackers who breached the outer walls still faced additional layers of fortification. The system functioned much like a modern defense-in-depth strategy, forcing enemies to fight uphill through successive barriers. The outer defensive circuit stretched for nearly 2 kilometers and incorporated more than a dozen towers. Each tower was positioned to support neighboring towers through overlapping fields of fire. Archers and crossbowmen could cover areas that would otherwise become vulnerable blind spots. Computer simulations performed on medieval fortifications show that overlapping defensive coverage dramatically increases survival rates during sieges. Yet the exact methods used by Genoese engineers to calculate these relationships remain unknown. There are no surviving blueprints. There are no surviving engineering manuals. The fortress itself is the only surviving evidence of the calculations. One of the least discussed mysteries involves measurement. The walls follow the irregular contours of the mountain while maintaining structural stability over long distances. Achieving this required accurate surveying. Modern engineers use laser scanners capable of measuring distances to within millimeters. Medieval builders relied on ropes, plumb lines, wooden levels, and geometric principles inherited from Roman and Byzantine traditions. The question is not whether these tools existed. The question is how such simple instruments produced results accurate enough to construct a fortress across steep volcanic terrain. Archaeologists studying medieval fortifications have repeatedly found evidence that builders possessed practical geometric knowledge far more sophisticated than previously assumed. Similar mysteries surround the construction of Carcassonne, the walls of Theodosian walls, and the mountain fortresses of the Crusader states. Sudak belongs to this same category of engineering puzzles. Water determines whether a fortress survives a siege. Food can be rationed, weapons can be repaired. But without water, even the strongest fortress eventually falls. Sudak sits on a rocky hill with limited natural freshwater resources. Historical records and archaeological investigations indicate the existence of large storage cisterns designed to collect and preserve water supplies. The engineering challenge was enormous. The Black Sea region experiences seasonal fluctuations in rainfall. During prolonged sieges, thousands of soldiers, civilians, and animals could require water every day. A single person typically requires at least 2 to 3 liters of drinking water daily under normal conditions. During military operations, requirements increase significantly. This means a garrison of only 1,000 individuals could consume several thousand liters every day. Researchers still debate the full capacity of Sudak's water storage network. Some believe extensive rainwater harvesting systems supplemented local springs. Others argue that additional supply routes may have existed outside the visible archaeological record. Whatever the answer, the fortress could not have functioned without sophisticated hydraulic planning. Perhaps the most fascinating engineering mystery of Sudak Fortress lies within the walls themselves. Many sections of the fortress were constructed during the Genoese period in the 14th and 15th centuries. More than 600 years later, substantial portions remained standing despite earthquakes, warfare, coastal weathering, temperature fluctuations, and centuries of neglect. From a materials science perspective, this is extraordinary. Modern concrete structures often require major maintenance after only a few decades. Steel reinforcement can corrode. Freeze-thaw cycles can crack masonry. Salt carried by sea winds can gradually destroy building materials. Yet Sudak continues to endure. The fortress was primarily constructed using local limestone and sandstone, bonded with lime mortar. At first glance, this appears simple. However, scientific studies of historical mortars across the Mediterranean have revealed surprising complexity. Many medieval builders mixed crushed ceramics, brick fragments, volcanic materials, and other additives into lime mortar. These ingredients could trigger chemical reactions similar to those found in Roman hydraulic concrete. Microscopic analysis of ancient mortars from Roman harbours has shown that certain mineral crystals continue strengthening structures centuries after construction. Researchers have discovered rare calcium aluminum silicate compounds that contribute to remarkable durability. Could similar processes have occurred within the walls of Sudak? Some material analyses suggest that medieval builders understood far more about mortar performance than written records indicate. The exact recipes, however, were rarely documented. Construction knowledge was often transmitted through apprenticeship rather than books. When master builders died, portions of their expertise disappeared with them. This pattern appears repeatedly throughout history. Roman concrete remains durable after nearly 2,000 years. The mortar used in parts of the Great Wall of China incorporated sticky rice compounds that improved strength. Medieval cathedral builders created structures that have survived for centuries despite constant environmental stress. Sudak Fortress may represent another example of lost materials technology. Scientists can analyze surviving samples, identify mineral compositions, and model chemical reactions. Yet, reconstructing the complete manufacturing process remains difficult because the human knowledge behind the materials has vanished. The walls still stand, the builders' methods remain partly hidden. Construction on Sudak's scale required an immense logistical operation. The fortress covers roughly 30 hectares and includes massive walls, towers, gates, defensive platforms, and internal structures. Every stone had to be quarried. Every stone had to be transported uphill. Every stone had to be positioned precisely. Today, cranes can lift dozens of tons with ease. Medieval builders relied on human labor, animal power, wooden scaffolding, pulleys, and lifting devices derived from ancient engineering traditions. Archaeologists estimate that large fortification projects often required hundreds or even thousands of workers operating over decades. Yet many questions remain unanswered. How was labour organised? How were materials supplied consistently? How were construction schedules coordinated? The fortress preserves the result, but not the process.
Takamatsuzuka Tomb sits beneath a quiet hill in rural Japan, yet inside this tiny stone chamber, archaeologists discovered something almost impossible. Vivid wall paintings that survived more than 13 centuries in one of the most humid climates in East Asia. Even more mysterious, the tomb contains astronomical maps, mathematically aligned architecture, and preservation techniques so effective that the paintings remained safer before modern archaeologists opened the chamber in 1972. For many researchers, Takamatsuzuka is not just a burial site. It is evidence that elite Japan during the Asuka period may have possessed engineering, chemical, and astronomical knowledge, far more advanced than historians once believed. The tomb was officially excavated in 1972 after local residents reported unusual stone formations beneath a circular mound about 5 meters high and 18 meters wide. When archaeologists opened the chamber, they found a compact stone room measuring only around 2.6 meters long, but its walls were covered with brilliantly colored murals unlike anything previously discovered in Japan. The discovery shocked historians immediately. Japan's humid environment normally destroys ancient pigments rapidly, especially organic binders and mineral paints. Yet the Takamatsuzuka murals still displayed clear reds, blacks, whites, and blues after roughly 1,300 years underground. The site was soon designated a special historic site and one of Japan's greatest archaeological treasures. The greatest mystery of Takamatsuzuka is not the tomb itself. It is the survival of its colours. Inside the chamber, archaeologists found paintings of court ladies, celestial beasts, and astronomical symbols rendered with remarkable precision. Laboratory analysis later identified pigments such as cinnabar for red, azurite for blue, and carbon black for dark outlines. These were expensive and technically demanding materials even by continental Asian standards during the 7th and 8th centuries. The problem is that pigments like azurite are extremely vulnerable to moisture and chemical instability. In modern conservation science, maintaining mineral pigments often requires tightly controlled humidity systems. Yet Takamatsuzuka survived naturally underground for over a millennium. Researchers discovered that the tomb chamber had been sealed with astonishing precision. The stone blocks fit together so tightly that airflow was drastically reduced. Oxygen levels inside the chamber likely remained unusually stable for centuries, slowing oxidation and microbial growth. In effect, the builders may have accidentally or intentionally created a primitive climate-controlled vault. What makes the mystery deeper is what happened after the tomb was opened. Within only a few decades, fungi and bacteria began attacking the murals. Black mold spots spread rapidly across several paintings, despite modern preservation technology. By the early 2000s, conservators were forced to dismantle sections of the chamber and move the murals into controlled laboratory environments. This led to an uncomfortable conclusion. The ancient sealing methods may actually have protected the paintings more effectively than the initial modern conservation attempts. Comparisons are often made with tomb paintings in Egypt's Valley of the Kings, or the cave murals of Dunhuang in China. But unlike Egypt's dry desert environment, Takamatsuzuka existed in humid Japanese soil with annual rainfall often exceeding 1,300 millimeters. From a preservation standpoint, the survival of these murals is statistically extraordinary. Some conservation scientists estimate that without an unusually stable microclimate, pigments in such an environment
should have deteriorated centuries earlier. Yet the faces, clothing folds, and color contrasts remained recognizable after 13 centuries underground. The tomb almost behaves like a sealed time capsule, engineered far ahead of its era. The chamber itself is another puzzle. Unlike ancient Egypt or Rome, early Japan was not famous for monumental stone engineering. Most major structures during the Asuka period were built primarily from wood. Yet Takamatsuzuka demonstrates stoneworking precision surprisingly comparable to Korean Goguryeo tombs and certain Tang dynasty burial chambers in China. The walls were assembled from carefully cut tough stone blocks with minimal gaps between them. Modern scans revealed remarkably flat joining surfaces, reducing airflow and water penetration. Some researchers argue that deviations between surfaces measure only a few millimeters in certain sections. This creates a difficult engineering question. How did builders working in a confined underground space achieve such accurate alignment without modern measuring tools? The tomb also raises logistical problems. Some stones weigh several hundred kilograms, yet there is little evidence of large-scale lifting systems or ramps. Moving heavy stone through narrow excavation corridors would have required careful planning and mechanical coordination. Even more mysterious is the balance between strength and isolation. The chamber remained structurally stable for over 1,300 years despite earthquakes, seasonal moisture expansion, and shifting soil pressure. Japan is one of the most seismically active regions on Earth, experiencing thousands of measurable earthquakes every year. Ancient builders somehow created a chamber capable of surviving this unstable environment for centuries. Painted across the ceiling is one of the oldest known astronomical representations in Japan. Golden star markers appear against a dark background, forming constellations connected to East Asian celestial traditions. At first glance, it resembles imported Chinese astronomical symbolism from the Tang dynasty, but closer examination revealed something more sophisticated. The arrangement appears intentionally adapted to the curved geometry of the chamber ceiling. This matters because translating a flat star map onto a curved surface without distorting relative positions requires geometric understanding. Even today, astronomers and cartographers deal with similar projection problems when converting celestial coordinates into visual maps. Some scholars believe the mural reflects direct transmission of advanced astronomical knowledge from China or the Korean peninsula. Others argue the Japanese court had already developed its own educated class capable of understanding celestial positioning for ritual, political, and calendrical purposes. The ceiling also connects to broader East Asian cosmology. Ancient rulers often linked political legitimacy to celestial order. In this sense, the tomb may have functioned not merely as a burial chamber, but as a symbolic model of the universe itself. The walls contain depictions of the four guardian beasts of East Asian cosmology: the azure dragon, white tiger, vermilion bird, and black tortoise. Each creature corresponds to a cardinal direction, a season, and a section of the sky. Their placement inside the tomb was not random. The orientation aligns closely with traditional cosmological systems used in China and Korea for geomancy and royal burials. This suggests the builders used astronomical observation during construction. Without magnetic surveying instruments or modern compasses, ancient engineers likely relied on solar positioning and stellar tracking to establish orientation. The precision is impressive considering the tomb's compact scale. Even small directional errors could disrupt symbolic alignment. Yet the chamber maintains a coherent cosmological arrangement that survived intact for centuries. The famous female figures painted inside the tomb may be the strongest evidence of cultural exchange across East Asia during the Asuka period. Their hairstyles, layered robes, facial proportions, and shading techniques strongly resemble Tang dynasty artistic traditions and Goguryeo mural painting styles.
yet the paintings were created inside Japan. This has led historians to debate whether foreign artists participated directly in constructing the tomb. Some theories suggest immigrant craftsmen from the Korean peninsula brought specialized painting techniques to the Japanese court. Others believe elite Japanese artists studied continental methods and adapted them locally. Either explanation points towards something larger: a sophisticated international flow of knowledge, technology, and artistic methods moving across East Asia more than 1,300 years ago. In other words, Takamatsuzuka may represent not an isolated Japanese achievement, but part of an interconnected scientific and cultural network stretching across ancient Asia. To this day, the identity of the person buried inside Takamatsuzuka tomb remains unknown. The sophistication of the chamber suggests the occupant may have belonged to the imperial family or an elite noble connected to Tang China or the Korean peninsula. Who do you think was truly buried inside the Takamatsuzuka tomb? A royal prince, a foreign noble, or someone whose identity was intentionally erased from history? Share your theories in the comments below.
Mary Gyal Kala, located in present-day Turkmenistan near the ancient Murgab River oasis, was once one of the largest cities on the Silk Road. Behind its massive mud brick walls lies a technological mystery that archaeologists are still trying to understand. How did ancient engineers build, supply, defend and industrialize a city in the middle of one of Central Asia's harshest environments nearly 2,000 years ago? The ruins of Gyal Kala were known to local populations for centuries, but systematic archaeological investigations began in the late 19th century and expanded significantly during Soviet expeditions throughout the 20th century. Modern excavations conducted by the International MERV project have revealed a vast urban landscape covering approximately 360 hectares, exposing evidence of sophisticated engineering, industrial production, and urban planning that exceeded previous expectations. At first glance, Gyal Kala appears impossible. The city was built primarily from mud brick, a material that modern engineers consider vulnerable to erosion, rain, temperature fluctuations, and wind damage. Yet large sections of its walls remain visible after nearly 2,000 years. The fortifications enclosed an area of approximately 4 square kilometers, and some surviving wall sections still rise more than 10 meters above the surrounding terrain. Archaeologists estimate that millions of mud bricks were required to construct the defensive system alone. The question is simple: how did builders working without modern chemistry create earthen structures capable of surviving centuries of warfare, earthquakes, floods, and desert weather? Studies indicate that the bricks were manufactured from carefully selected clay-rich sediments combined with organic materials. However, researchers still debate the precise composition of the mixtures and the engineering principles behind their remarkable durability. Similar questions surround other ancient earthen structures such as the walls of Babylon and portions of the Great Wall of China. Yet Gyal Kala presents an even greater challenge because it survived within an environment characterized by extreme temperature variation and powerful seasonal winds. The builders clearly understood properties of soil stabilization long before modern geotechnical engineering emerged, although exactly how much they understood remains uncertain. Viewed from above, Gyal Kala reveals another puzzle. The city was constructed with a remarkably regular plan, and massive defensive walls form a near-rectangular enclosure stretching approximately 2 kilometers from side to side. Creating such a design required more than construction skill, it required surveying. Today, engineers rely on laser instruments, satellite positioning systems, digital terrain models, and advanced measurement equipment, Yet ancient surveyors possessed none of these technologies. Even so, they successfully laid out enormous walls, aligned gates, organized streets, and coordinated large-scale construction projects across hundreds of hectares. The challenge becomes even more impressive when considering the city's multiple construction phases. Archaeological evidence indicates that successive generations repeatedly reinforced, expanded, and modified the fortifications while maintaining overall structural coherence. This level of long-term planning suggests the existence of technical traditions passed from one generation to another. The buildings survived, but the manuals that explained how to build them did not. No city can exist without water, and this creates one of Giarkala's greatest mysteries. The city stood within the Murghab Oasis, surrounded by landscapes that today appear semi-arid and unforgiving. Summer temperatures regularly exceed 40 degrees Celsius, rainfall is limited, and agriculture without irrigation would have been impossible. Yet historical records indicate that Merv supported populations numbering in the tens or perhaps hundreds of thousands during various periods of its history. Such numbers required extraordinary quantities of water. Researchers have identified traces of ancient canals connected to the Murghab river system. These channels transported water across vast distances, supporting agriculture, industry, and urban life. However, much of the original network has disappeared. Sand accumulation, river migration, erosion, and centuries of human activity have erased significant portions of the hydraulic system. The remaining evidence raises difficult questions. How were gradients calculated? How was water flow regulated? And how are canals maintained across enormous distances? Hydraulic engineers understand that even small errors in slope can cause catastrophic failures in irrigation systems. Excessive slope accelerates erosion, while insufficient slope prevents water movement. Ancient engineers somehow achieved a balance precise enough to sustain one of Central Asia's most important urban centres, yet their calculations remain largely invisible. Among all the technological enigmas of Giarkala, none may be more surprising than its industrial zones. Excavations conducted by the International Merv Project uncovered evidence suggesting large-scale metallurgical activity inside the city. What archaeologists found was not merely a collection of small workshops, they discovered an organized industrial landscape. Several furnace complexes, slag deposits, ash layers, production debris, and specialized working areas indicate that metal production occurred on a scale far greater than previously assumed. This discovery transformed how researchers viewed the city. For decades, Giarkala was primarily regarded as a commercial and administrative center along the Silk Road, but the industrial evidence revealed something else. It was also a manufacturing center. The furnace remains suggest that ancient metallurgists possess sophisticated knowledge of airflow control, combustion management, and high-temperature production processes. Producing iron and steel is far more complicated than simply heating metal. Ancient craftsmen had to maintain temperatures approaching or exceeding 1,100 to 1,300 degrees Celsius, depending on the process. Achieving such conditions consistently required careful fuel selection, furnace design, and oxygen management. Without thermometers, pressure gauges, or laboratory equipment, metalworkers relied entirely on experience and observation. Yet the archaeological evidence suggests remarkable consistency. Some furnace structures appear to have incorporated controlled air intake systems that improved combustion efficiency. Researchers have identified evidence of tuyères, ceramic air nozzles used to direct oxygen into furnaces. This technology dramatically increases achievable temperatures, and the same principle remains fundamental in modern blast furnace operations. The mystery deepens when examining production scale. Certain industrial zones contain substantial accumulations of slag, the waste material generated during metal extraction and refining. Large slag deposits typically indicate repeated production cycles over long periods, suggesting organized manufacturing rather than occasional local metalworking. But where did the technical knowledge originate? Some scholars propose influences from Persian metallurgical traditions, while others point to connections with technologies moving along Silk Road trade routes from India, China, or the Near East. No consensus exists. Even more puzzling is the possibility of still production. Several researchers have suggested that certain furnace remains may have been capable of supporting advanced iron working processes. If true, Gjorkalla's craftsmen would have belonged to a technological tradition comparable to some of the most sophisticated metallurgical centers of the ancient world. For comparison, Roman iron production centers in Europe, Parthian workshops in Iran, and Indian steel-making traditions all required highly specialized expertise. The craftsmen of Gjorkalla appear to have possessed similar capabilities, yet almost nothing is known about the individuals themselves. Their names are lost, their methods are lost, and only the industrial scars they left in the ground remain. Gjorkalla was more than a fortress or industrial center. It was a crossroads of civilizations. Archaeologists have found evidence of Zoroastrian, Buddhist, Christian, and Islamic communities, reflecting centuries of cultural diversity. This mix of cultures may explain the site's technological sophistication, as ideas and innovations traveled along the Silk Road through trade and migration. Gjorkalla may have served as an ancient hub for knowledge exchange, though exactly how this technology spread remains unclear.
Madinat al-Zahra was once the most dazzling city in Western Europe. Built in the 10th century by the Umayyad Caliph Abd al-Rahman III, near Córdoba in southern Spain, the palace city reportedly shimmered with marble gold, pools of liquid reflections, and halls engineered to manipulate light itself. Then, less than 80 years later, it vanished into ruin. Today, more than 90% of the site still remains buried underground, and archaeologists believe some of its most advanced engineering secrets may still be hidden beneath the hills outside Córdoba. The ruins of Madinat al-Zahra were rediscovered in 1911 by Spanish archaeologist Ricardo Velázquez Bosco after centuries of local legends describing buried palaces beneath the farmland west of Córdoba. Excavations soon uncovered massive reception halls, carved marble columns, hydraulic systems, gardens, and fragments of decorative stonework so refined that many historians compared them to Byzantine imperial architecture. What shocked researchers most was the scale. Historical records suggest the city covered nearly 112 hectares, making it vastly larger than most royal complexes in medieval Europe. Yet only around 10% has been excavated, meaning the overwhelming majority of the city, including possible workshops, underground conduits, and ceremonial sectors, remains unexplored. One of the greatest mysteries surrounding Madinat al-Zahra is how quickly it was constructed. Historical texts claim thousands of workers operated continuously, with as many as 10,000 labourers and over 1,000 animals transporting stone and materials every day. Some chroniclers describe construction progressing at a pace almost unimaginable for the 10th century. Entire palace sectors covered in marble and intricate carvings appeared within decades. Compared to contemporary European cities, the contrast is staggering. During the same period, much of Western Europe was still dominated by relatively small stone fortifications and timber structures. Yet Madinat al-Zahra featured sophisticated urban planning, formal gardens, terraced architecture, advanced water distribution,
and monumental ceremonial spaces designed with mathematical precision. Historians often compare Cordoba itself to Constantinople because both cities possessed paved roads, public baths, libraries, and hydraulic infrastructure at a level rarely seen elsewhere in Europe at the time. The city's water engineering remains one of its most technically mysterious features. Madinat al-Zahra was built on a sloping terrace system along the foothills of the Sierra Morena Mountains. Engineers used gravity-fed hydraulic channels to distribute water across multiple elevations, powering fountains, reflective pools, irrigation systems, and palace baths simultaneously. Archaeologists discovered ceramic pipes, underground conduits, reservoirs, and carefully angled channels with gradients so precise that some vary only slightly over long distances. Maintaining stable water pressure across a terraced complex in a semi-arid climate would have required extraordinary calculations. Modern hydraulic engineers studying the ruins noted that even small deviations in channel slope could have disrupted flow rates entirely. Some researchers compare the engineering challenge to Roman aqueduct systems, yet Madinat al-Zahra integrated these hydraulic mechanisms directly into ceremonial architecture. Water was not merely functional, it became part of the visual illusion of power. But the most fascinating mystery of all may be the city's manipulation of light. Medieval Islamic chronicles described halls where sunlight shimmered across polished marble and metallic surfaces so intensely that visitors believed the rooms were moving. One famous account described a reception hall containing reflective pools and decorative materials that caused light to ripple, like lightning across water. For years, many historians dismissed these descriptions as exaggerated royal propaganda. However, archaeological evidence increasingly suggests the architects of Madinat al-Zahra may have intentionally engineered optical effects through the strategic placement of reflective materials and sunlight angles. The palace complex used enormous quantities of white marble imported from North Africa and other Mediterranean regions. White marble possesses high reflectivity, especially under the intense Andalusian sun. Combined with polished stucco, glazed ceramics, reflective pools, and metallic decorative elements, the architecture may have functioned almost like a massive optical instrument. Some halls appear carefully oriented to maximize natural illumination during specific times of day. Researchers studying solar movement at the site observed that sunlight entering through arches and openings could strike polished surfaces at controlled angles, dramatically amplifying brightness inside ceremonial chambers. This phenomenon resembles principles used in modern architectural lighting design, where reflective materials manipulate perception and emotional response. The so-called rich hall, one of the most luxurious structures excavated at the site, demonstrates this especially well. Its carved vegetal patterns, geometric reliefs, and polished surfaces create constantly shifting shadows as sunlight moves throughout the day. The effect is surprisingly dynamic. Instead of static decoration, the hall appears visually alive. Some scholars suggest the architects understood how sunlight interacted with carved depth, reflective surfaces, and water reflections to create psychological impact. Even more intriguing are historical descriptions mentioning pools filled with mercury or highly reflective liquids capable of producing moving flashes of light. While direct archaeological proof remains inconclusive, similar reflective experiments are documented elsewhere in medieval Islamic engineering traditions. If true, Madinat al-Zahra may have employed deliberate sensory manipulation centuries before modern theatrical architecture existed. The precision of the decorative stonework adds another layer to the mystery. Thousands of carved marble fragments recovered from the site display astonishing symmetry and consistency. Floral motifs repeat with near-identical geometry over massive areas. Historians studying the carvings have questioned how artisans working entirely by hand achieved such standardization on such a large scale. Some experts believe the craftsmen used advanced geometric templates and modular design systems far more sophisticated than typically associated with 10th century Europe. Islamic mathematicians during this era were already developing complex geometric theories, including tessellation principles that would later influence Moorish architecture across Spain. Certain repeating patterns at Madinat al-Zahra display mathematical regularity comparable to later Islamic masterpieces such as the Alhambra in Granada. The logistics behind the city remain equally astonishing. Historical accounts mention marble columns arriving from Tunisia, Italy, and even Byzantine territories, transporting thousands of heavy columns across the Mediterranean and then inland to Cordoba would have required immense coordination. Researchers estimate some columns weighed several tons each. Moving them uphill into the terraced palace complex without modern machinery remains difficult to fully reconstruct. Archaeologists are also puzzled by the speed with which the city disappeared. Around the early 11th century, civil war erupted across Al-Andalus during the Fitna period. Madinat al-Zahra was looted, burned, dismantled, and gradually abandoned. Valuable marble and columns were stripped away and reused in later structures throughout the region. Over centuries, the ruins were buried under soil and forgotten almost completely. Yet despite the destruction, modern surveys indicate vast sections remain untouched underground. Ground-penetrating radar has identified buried walls, foundations, and unexplored sectors extending far beyond the excavated areas. Some researchers suspect hidden hydraulic chambers, workshops, or ceremonial structures may still survive beneath the landscape. What do you think is still hidden beneath Madinat al-Zahra lost technology, forgotten engineering knowledge, or something even more mysterious? Share your thoughts in the comments below.